Okay, folks, welcome back. Here we are in the course on bioethical issues at the beginning of human life within the Master of Science in Bioethics at St. Thomas University. Beginning always with a little prayer in the name of the Father, the Son, and the Holy Spirit. Come, Holy Spirit, fill the hearts of your faithful and kindle in us the fire of your divine love. In a very special way, we pray today for those people who are in most need of your divine mercy here in the United States and throughout the whole world. This we ask in the name of Christ our Lord. Amen. All right, so any questions or comments from previous lectures?
I have a question.
Yes.
I was wondering if you could explain the principle of double effect once more, because
Yes.
I'm having a hard time understanding salpingectomy and salpingostomy.
Yes.
Yes, the difference between the two and how one is justifiable and one isn't, if at the end of the day their results are the same. And I understand that, intent is important between the two. However, the benefits between the two, I'm just, if you could just explain that once more for me.
Absolutely. Yes. Thank you. Thank you for raising the question, Chris, because it is a delicate subject. Let me bring up double effect here. Let's see where I have it. Here we go. Okay. Yes. And the end result is the same in the sense that with both procedures, either salpingectomy or salpingostomy, the embryo dies. The embryo ends up dying, okay? So from that perspective, the end is the same. But the means that are used are critical when we do principled bioethics, because the means also have to be justified in themselves. Now, this is a point that is subtle, if you will, and some people have to reflect a little bit on it, because many times we're not used to it in the general culture, all right? Because frankly, I've been in this world for 68 years now, and over the decades, what I see is that what is prevalent is utilitarian, just a pragmatic mentality. We're very practical in the US and in many parts of the world. And so, but it's subconscious. It's just filtered into our mindset, and kind of by default, we look at issues in a very pragmatical way. We say, well, the end result is the same, so the means are kind of secondary as long as it gets us there. Also, obviously, as long as it's legal, so that we don't break any laws. But here, with principled bioethics, we focus especially on the means, because the means themselves have to be justified. In other words, the procedures, the protocols that are used for obtaining that result. And that, by the way, is very important, for example, in certain fields and certain professions where protocols there are many different protocols to be implemented. For example, in the practice of medicine, it's all by protocol. Every doctor, every medical doctor that practices medicine with their patient, they don't invent stuff. They don't invent procedures and protocols on the wing, as they say. For each patient as they show up, a patient shows up and has a pain on the side, says, well, doctor says, okay, well, let's try this. Let's try this medication. That's what we're trying to. No, there are particular protocols that are followed. It's almost like a recipe for making some kind of a food that we're preparing or baking, for example. There are procedures. The flour has to be mixed with water and to make the dough before we put the dough into the oven. We can't just put the flour without just the powder into the oven, right? So there are procedures to follow, and those procedures are the ones that we focus on to see if the procedure itself, if the protocol is ethical or not, if it's respectful of human dignity. Okay, so I want to say that as an introduction, as a background. Now, let's look at the protocol itself, this double effect, because it's very succinct, okay? We have two effects, two results coming from the one procedure. And one result is what we can say a good result, and the other one is a bad result. In other words, speaking with regards to the result itself. And so when we consider ectopic pregnancy is any pregnancy that is not occurring in the endometrium, in the uterus, all right? And so what happens is that other parts of the body are not equipped to handle a pregnancy, to handle a placenta, for example, that is highly vascularized. And if that ruptures, then it's going to cause a massive hemorrhage for the woman. And so any embryo who implants anywhere else other than the endometrium, the lateral walls of the uterus, that is a high risk pregnancy on the woman. Okay, it's considered a high risk medically, clinically. And so the first thing that is done is expectant observation, expectant monitoring. Expectant meaning that the doctor who is monitoring that pregnancy has to be ready to act on a moment's notice if the pregnancy does not resolve by itself. And so, what do we mean that the pregnancy resolves by itself? An ectopic pregnancy. What do we? Let me stop and ask some questions and do this in a Socratic way so that I ask questions and see if people are following. When an ectopic pregnancy resolves by itself, what are we talking about? That?
One.
Right, either a miscarriage or technically, we can even be a little more sophisticated than that in the sense or precise than that, because remember, miscarriage typically is when we already have a fetus, which is after 8 weeks. All right, but 8 weeks is already, we're talking about an inch-long embryo who is now going to grow very fast because all the major organs are in place in miniature. And so now in 7 months, that embryo has to grow from 1 inch to 1 foot, all right? And so that's a critical time when you think about functionally, right? I keep saying think functionally. Let's get ourselves inside that embryo. We are the embryo. And in 7 months, we have to go from 1 inch to 1 foot. That's drastic, that's dramatic. We're going to suck a lot of nutrients from that mother. That placenta is going to expand and invade the maternal tissue big time. So that's the big danger. That's the danger of causing the hemorrhage right there, right? Therefore, by the time we get to the 2nd month, that if that pregnancy has not resolved, definitely it has to be a surgical intervention, okay? So let's front end it more in the first couple of weeks, let's say within 1 month. Within 1 month, so we're talking about instead of a miscarriage, the technical term would be a type of abortion, but it's, yes, Chris?
Spontaneous abortion?
Exactly, it's a spontaneous abortion. It's also a technicality, but that shows also when we speak in that language, we show competence. We show to the other people that we know what we're talking about. So really, it's a spontaneous abortion, right? That will be when the tissue of the mother took care of the problem. That baby died, that embryo died, and then there are 2 options. Either the remains, the tissue that remains, the dead embryo is discarded, right? Or sometimes is reabsorbed, actually reabsorbed, because again, nature is economic. And what the tissue, the mother tissue is saying, oh, look, here's extra tissue, I can reabsorb this because these are dead cells. And our cells are dying all the time. You know, we're shedding skin all the time. When we shower, if we were to look at the remains of the shower, we find millions and millions of cells. They're mostly skin cells that are dead. We have layers of dead cells on the outside of our body, but we also have layers of dead cells on the inside of the body. So all the organs are regenerating continuously. And those dead cells, dead liver cells, dead kidney cells, and so forth, are being recycled. We can even get down to the cellular level. There are little bags inside the cell, one of the organelles. They're called lysosomes, right? Soma is a reference to body, like chromosome, colored bodies. Lyso is a reference to lysis, which means breaking up. So when something lyses, something breaks up, right? So these little lysosomes, the little bags, and what do they contain? They contain enzymes, particular enzymes that are
Degrading.
exactly digestive enzymes. There are proteases, most of them are proteases, right? Enzymes that digest proteins and other types of enzymes. But those little bags, it's important that they maintain integrity, because when that bag bursts, that cell is going to self-digest. Self-digest. And remember, nature never forgives. All right, so a broken lysosome is going to do its thing, which is going to digest everything that's around it. And so we see that there is a process of recycling dead tissue inside our bodies. That's a good thing. All right, so we have all that biological background in place. We understand it well. And then we can look a little bit, we can go on a probabilistic model here and say, there is this expectant observation of the mother, expectant monitoring, because what's the percentage of ectopic pregnancy that's self-resolve? Approximately, anyone remember the percentage?
20.
85 to 90%. That's a high percentage, right? Okay, and so that's a good thing. The body takes care of that, all right, because the body knows this embryo is growing in the wrong place. And the embryo himself or herself also realizes biochemically, this is all biochemical signaling. There's no brain on the embryo yet, okay? But by biochemical signaling, that it's the outer layer of the blastocyst. Remember the trophoblast that will become the placenta? That trophoblast realizes it's implanting in the wrong place, and it's getting signals of resistance from the surrounding tissue that is not endometrial. Okay, so all that works in concert to try to avoid the continuation of that pregnancy. So that pregnancy is terminated naturally and taken care of by the body, either by discarding, spontaneous abortion, or by reabsorption. Okay, then we have the other 10%, that is the challenging one, all right? So the 10% that doesn't resolve, and that's where the doctor has to be monitoring that carefully, including ultrasound. And if that little, what would look like a cyst, right? It would look like a little bubble, a little ball, a little mass. It would be looking like a little tiny tumor to begin with. If that little tiny tumor is growing, right? It's not malignant in the sense of cancerous, but it's analogous, it's equivalent. It's a cell growth and tissue growth in the wrong place, all right? So, whereas it's not cancerous, it is malignant in the sense that it's growing in the wrong place. Okay, so we understand that. What to do? There has to be an intervention. In fact, there's a third option. So actually there are two options, either surgically or chemical. There's also what is called a medical intervention, which is not surgical, is medical. I didn't mention it because it's a little too much detail, but since this particular lecture today may be a little shorter, we actually have some time providentially. Methotrexate is another option that is chemical, medical, non-surgical. Let me just put the spelling here. Methotrexate, okay. And we'll get to it in a minute, but let me go through the classical scenario first before we go to this new scenario. All right, so let's say it's tubal, it's in the fallopian tube, which is again the large percentage of them, 80 to 90% in that area. And from that perspective, it's a little easier one to intervene surgically. We have the two options. We have either the option of removing the tube or the option of removing the embryo directly, right? So everyone's on board here. All right, now here's where it gets tricky philosophically and anthropologically. So we need to, again, be on the same page with regards to the anthropology. In other words, our understanding of the human embryo. What I talked about, what is the ontological status of the human embryo, all right? What is the status of being? What kind of being is it? What kind of being is it? So it's material because there are cells there, so there's matter, all right? And this matter, what is this matter? It's not just an organ, it's not just a tissue, it's an actual individual, it's a human being. That's why I took a lot of biological pains at the beginning of the course to explain and to give the foundation, the scientific, biological, natural foundation for the fact that the zygote already is a new individual of whatever species, including the human, we're no exception. So if it's a new individual, then it's a new being, all right? And in the case of the human, it's a new human being. At fertilization, completed fertilization, syngamy, all that, all right? So with the background that from the zygote forward, we have a new human being. Ontologically, in other words, in himself or herself, as human as the rest of us, because certain categories do not accept a gradation. What do I mean by gradation? What's a very common example of gradation that we're experiencing now? Let's say it's been in the news for the past few days throughout the whole United States. Half of the United States, over 150 million people, have been tragically affected by what? The weather, power outage. People are dying because they don't have electricity to heat themselves up. They're literally freezing to death, you know, and so forth. So, but that accepts gradation in what sense? In the sense that the temperature is not either very hot or very cold. There's degrees of temperature. From the very comfortable to the slightly uncomfortable on either side to the very uncomfortable on either side, right? But there is a gradation there. So temperature is a gradient. Many things are a gradient. Humidity is a gradient, et cetera, et cetera. But humanity is not a gradient in the sense that we're not more or less human. If we were, okay, and always when one principle is kind of not too clear, Aquinas had a little mental exercise. He said, look at the opposite and see if that makes sense. Okay, so let's look at the opposite if humanity had gradation. It means that some people would be more human than other people, right? And then also some people would be less human than other people. That's beginning to sound very discriminatory. Then the next question is who decides? Who is more human and who's less human? Because in fact, if we go back about 500 years, that was used actually in legal courts to defend the enslavement of some people by other people, because those people were considered less human than the others, okay? And in fact, it was based even on actual evidence, if you will, in the, this gets very sensitive, but this is just pure, honest history, all right? When we compare what was happening, let's say in the 1500s in Europe with what was happening in Africa in the 1500s. What do we have? In Africa, we have basically a tribal system of fairly kind of, I want to say easy lifestyle in the sense that because it's mostly tropical, the produce, the agriculture and the animal husbandry and so forth was fairly easy, all right? So it didn't take much effort to stay alive, number one. Number two, because it was tropical, there wasn't much clothing needed either and so forth. So people basically went around with scant clothing. When you compare that to Europe, with the hardship of the winters, all right, and the seasons, that imposed on the European population an effort to survive better, so to develop clothing and more clothing and better clothing. That also led to a trade, all right, which stimulated itself into even better type of clothing and so forth. So that progressed, but also in the culture also progressed in the sense that they had, for example, polyphony singing. They developed instruments, they developed wind instruments, they developed percussion instruments, string instruments for music, and the music became very elaborate. And really, when you hear Renaissance and Baroque music, it's just naturally pleasing to the ear, polyphony and so forth, all right? Big contrast with the cultural milieu of what was happening, let's say, in tropical Africa. Look at the architecture. Again, because they had, in Europe, there was a lot of stone available because of the mountain regions and so forth, and marble and other stones, then buildings were basically built out of stone, also because they suffer more earthquakes in general, so the buildings had to be more solid, stronger. And then the trade again gets into it, and the different guilds competing with each other. We end up with churches and cathedrals in the Gothic style, like Notre Dame de Paris, for example, or in the Renaissance style, like the Vatican, all right, St. Peter's Basilica, in contrast with tropicalized Africa, where it was mostly soil instead of stone, and those guilds were simply not developed in that style, more on the wood style and so forth, because it was not needed for a basic survival. So the end result is that those two cultures were so contrasted with each other that one culture actually thought that they were superior to the other, and therefore they justified in courts, in legal courts, the enslavement of the African people because they were considered less human. And now today, to us, looking back 500 years, that is absolutely revolting and abhorrent, right? But in the culture of the time, that's what's going on. Why? Because the Europeans made the anthropological error of putting gradation in humanity. And then it was precisely the church and the thinking, the philosophy and the theology of the church that started to complain about that and said, no, humanity does not accept gradation, because then precisely we're going to fall into this fallacy that some humans are more human than others. And then the end result is going to be enslavement and other kinds of subjugation, right? So we understand that today, but we understand it mostly for the born. The task that is still ahead of us, in my opinion, is to be consistent, an argument of logical consistency, to apply it also to the unborn, because their only handicap, let's say, is time, is that they're less mature than we are. But that doesn't mean that they're less human. If they were, then to be consistent, we would have to say that a baby is less human than a teenager, and a teenager less human than an adult, right? Which again is revolting and abhorrent because it is against the fundamental principle and value of human life. So, making the argument exhaustively that the human zygote is as human as you and I, and therefore I actually challenge all my students always to call the human embryo he or she, because that personalizes the embryo. When we call the human embryo it, we are already depersonalizing, and we fall into that pit. I've heard speeches by pro-life, very strong pro-lifers, okay, who talk sometimes unwittingly, they talk about the human embryo as it, just in the speech. It is human, they'll say. Well, you just dehumanized that human by calling him or her it. But you start referring to the human zygote or the human blastocyst as him or her, you're gonna get attention because, what do I mean him or her? Yeah, and we can do that, absolutely. Why? Because the sex is determined at fertilization. So if there's fertilization, there's either a male or a female. And again, it's a universal principle. It's not just a human. That's my whole point. This occurs with the giraffe, with the orangutan, and with plants, even with plants. Male and female determined at fertilization, right? So, all right. I think I've made my point exhaustively. We have a human being. That's little tiny blastocyst who is growing in the wrong place is a human being, all right? And therefore, we just don't have the right to intervene directly on the life of that human being, because it would be equivalent to taking a knife to any one of us, just taking out a machete or a scalpel, your preference, or a sword, a two-edged sword, and just hack away at a born human being. That's what salpingostomy does. Opens the tube and goes after the embryo. Yes, for the good, very good end of saving, in quotations, saving the fertility of the woman. And then the devil is in the detail in that that slit may also scar on the inside. And we're talking about microscopic because the blastocyst is still microscopic, about 10 microns in diameter, right? And so even if that scar is microscopic, which I will not see when I'm sewing, plus it's on the inside, right? Unwittingly, that slit may be the cause of a second ectopic pregnancy. So we have to be careful here. We have to be, aware of the clinical stuff that's going on. But let's assume somehow that tissue will recover, the inside of the tube will recover 100%. Okay, it's the same argument, it's an analogous argument to the pill. Let's assume that the pill doesn't have any of those side effects at all. It would still be the intrinsic evil aspect of it, all right? So here, excuse me, with salpingostomy, we're going after the embryo. So we're actually killing the embryo. We're killing a human being directly. In other words, that is, you see, and it says here, the good effect must not be obtained by means of the evil effect. We take care of the pathology. In salpingostomy, we take care of the pathology of the ectopic pregnancy by killing the embryo. So in fact, it violates the second point. The good effect, saving the life of the mother, is obtained precisely by means of killing the embryo. Follow? Which is unacceptable, unacceptable. In other words, we have to, all 5 points have to stick. Now, it's hard because what do we have? In salpingectomy, we know that the embryo is going to die. Of course, you take out that tube and the embryo's inside, it's very obvious that the embryo is going to die. And we already talked about the possibility of reimplanting and so forth, and the high risk there, and whether we have a chance or not. So the science is still open on that. We know the science is still open on reimplantation. But in the meantime, we have this current pathology that is progressing and on a daily basis may be the difference between the life and the death of the mother. So we can't just be dialing around. We have to have a preset answer, all right, as that pregnancy is progressing. It's not going to stop and wait and say, oh, okay, these guys are thinking about it, so pregnant embryo, let me just stop here and arrest and go into suspended animation until they figure it out. No way. Nature doesn't forgive. Nature will continue. That trophoblast will continue to invade the mother's tissue, seeking to establish a placenta, a fully functional placenta. All right. So salpingectomy. The tube is pathological, essential to declare that tube pathological, which it is, right? The tube itself, because it has this embryo growing in the wrong place. So the tube is pathological. The tube has been invaded by a trophoblast seeking to establish a placenta. There is a justification to remove that pathology, okay?
I'm sorry, I have a question.
Yeah, okay, excellent.
So in salpingostomy, why is the embryo not viewed as a pathogen in the sense where that has to be removed? Because if it stays there and grows there, then it'll eventually cause a problem for the woman.
Yes, excellent, excellent. So we're getting down to the nitty gritty. And by the way, I want to point out how much we are conditioned by subconscious categories. Because in your stating the question, which is an excellent question, twice you mentioned the embryo's it. We are so conditioned. If you follow, it will cause, when we say he or she will cause, changes the quality of that statement. But you follow me? We are so conditioned that it's there. And I've done it. I've done it in pro-life talk. Okay. So anyway, a little parenthesis. That's how attentive we have to be in bioethics. It's amazing. All right. So anyway, very excellent, because consider this. Is the embryo a tumor? Is the embryo a parasite? That is an argument that has been made by a number of pro-choicers to justify certain abortions. And it comes out of the camp, let's say, that a woman has a right to her body. Absolutely. A woman has a right to her body. A man has a right to his body, right? But the point is that if we start looking at the embryo as a tumor, then that's not biological, because a tumor doesn't have a brain. A tumor doesn't have organs that are functional, that is growing normally, right? A tumor is abnormal cell growth. So by definition, by medical, biological, clinical definition, an embryo who is growing normally as the embryo, in the wrong place, but growing normally, precisely, then that embryo is not a tumor. Okay, very important anthropologically, because a tumor is a part of the tissue of the woman, the man, whoever, whatever organ is whatever human is growing the tumor, that tumor is part of his or her tissue, right? Okay, so not a tumor. The other alternative would be, well, how about a parasite? Because the parasites are whole, intact, and they have their own individuality and so forth. They have their own ontological integrity. Okay, parasites do. But parasites, what do? Parasites, first of all, typically parasite is from another species invading a host of a different species. Okay, we normally don't have parasites parasitizing on their own species. They parasite other species, number one. So the embryo is the same species as the mother. Number two, the parasite brings no benefit to the host, and many times ends up killing the host. Well, we can argue that the embryo is going to kill the host in an ectopic pregnancy and so forth. But it's just in the wrong place. It's in the wrong place. To look at the human embryo as a parasite, all right, it's a very dangerous model, because it basically comes out of an antagonistic model, that we are against each other, all right? That for example, a mom who is pregnant, that pregnancy is against her. To think of the human embryo as a parasite is an antagonistic model, where it puts the embryo, the child, against the mother, and vice versa. That is a very dangerous, because then basically every relationship would be in principle antagonistic, all right? Whereas rather, there is a commensalism, and there is an alternative in biology, thanks be to God, which is called commensalism. Commensal is mutual benefit. One example that comes to mind right away is the zooxanthellae. Do people know what zooxanthellae is? Okay, well, it's from corals. It's what gives corals their color. Zooxanthellae. Okay. Zooxanthellae are algae that live inside corals. The coral polyp, all right? The polyp itself is transparent, translucent. The tissue of the coral itself is translucent. But it turns out that these algae get encrusted, absorbed into the polyp and they are not digested away, they're not eaten up, right? They survive in there because they provide some benefit to the coral. Now the coral, is a coral a plant or an animal? Basic biology from high school, they're coelenterate, right? So they are animals. They look like plants because they form these colonies, okay, and the branching and so forth, but they're definitely animals. The coral themselves, the polyps, all right? They're from the family of the jellyfish, the medusa, the hydras, and so forth. These are coelenterates or cnidarians. But they have established a commensalism with algae, typically brown algae, that get encrusted, embedded into the polyp itself, into each individual polyp. And because the polyp is translucent, the polyp itself allows light to go through its tissue. And what does the algae do? Now, are algae plants, animals? They're on the plant side. They photosynthesize. They photosynthesize. So these algae, these brown algae, they are producing glucose, which is nourishment for the polyp. What does the polyp offer the algae? Well, mostly a place to be, a location, all right? And some protection, so it doesn't, otherwise the alternative of these zooxanthellae is to float in the phytoplasm, in the plankton, right? Microscopic organisms that float in the plankton, and being plants, there will be phytoplankton. So it's equivalent to grass. They're going to be eaten by the zooplankton. And so being inside the coral, the zooxanthellae get protection, get a location and a protection. And so it's a commensalism. It's a mutualism. They both benefit, all right? Similar is the human embryo to the mom. We just have to look at it into the bigger picture that moms certainly survive pregnancy. The vast majority of moms are not killed by the pregnancy, okay, unless it's very late in their lives. But the vast majority of women have children, and we are the witnesses. The 8 billion people that we are in the world are witnesses that our moms, survive our pregnancy. And so it's a mutualism, okay, and it maintains the species. So it's a beneficial relationship, mutual beneficial relationship. Again, the tragic reality of the ectopic pregnancy is that that embryo is going in the wrong place. It's growing in the wrong place. Let me get back then to your question. I don't know if I've really provided an adequate answer or insight, but the embryo can never be considered as a parasite because we have then dehumanized that embryo. Okay, we have made that embryo an object. It's not another species, the same species, but we can never consider the human embryo as a parasite. Very important, it's really not biological. It's not sustained by the biological facts of human embryology or any embryology, all right? A pregnancy in any species, move it over to the hippopotamus or to whatever favorite mammal you have out there. That pregnancy can never be considered a parasite, all right? It's rather a commensal, it's a mutual relationship. It's a commensalism. I don't know, Chris, are you following?
I am following.
Okay. It's challenging. I see it's challenging because the end result, we keep focusing on the end result. That embryo is going to die. If we remove that tube, that embryo is going to die. But we have not intervened on the embryo. Okay, we have not intervened on the embryo. We have taken care of a pathology. And so we say with double effect that the evil effect, that the bad effect is foreseen. We can predict it, you know, and I can bet my bottom dollar in a sapingectomy that the embryo is going to die unless we attempt reimplantation. It's tragic, it's sad. We weep, we mourn. The woman, the mother, may actually mourn because she's losing that pregnancy. She wanted that child, okay? but we did not intend it, we did not desire it. Our will did not engage in killing that embryo, all right? I mean, if you want to put it graphically, the surgeon, if the surgeon is pro-life, as the surgeon is doing a salpingectomy, well, for a surgeon to do a salpingectomy instead of a salpingostomy, actually the surgeon would have to be pro-life, because the practical thing is to do a salpingostomy and preserve supposedly the fertility of the woman intact, you know, instead of cutting it down to 50%. All right. So automatically, a surgeon doing a salpingectomy is telling you it's a pro-life doctor. So I can see that doctor weeping as she or he is doing that operation because she doesn't want the death of this child, of this baby, of this blastocyst. It's foreseen, but not desired, not intended. Now, think of the converse in salpingostomy. How can I, surgeon, perform a salpingostomy, take out that embryo, scrape that embryo, if I do not want to scrape the embryo? If I don't want to kill the embryo, how can I scrape the embryo? I have to necessarily want to kill the embryo to scrape the embryo out of the tube. You see? Because assuming that the surgeon is not schizophrenic, all right, and can desire two opposite things at the same time, the surgeon doing a salpingostomy has to desire the killing of the embryo, necessarily. Unless we become so schizoid that saying, oh no, I'm just scraping, you know, give you a graphic example on two born humans. So I have a human in front of me and I have a machete on my hand. And I'm saying, oh no, I'm not killing that other human. It is my hand that is inserting a metal blade into the abdominal region of this other person in front of me. You know, well, yes, when we describe that act, that is called killing. All right. So I can describe the detail of my hand inserting a metal object into the abdominal region of another person in front of me, but that in one word is called killing. All right, unless my hand is acting involuntarily, but who's moving the hand? St. John Paul II, when he worked, before he was a priest, when he was studying in the seminary, hidden from the Nazi regime up in the, or the communist regime in the quarries, the marble quarries, all right, where they were sent to work, the workers would protect him and he would go study theology because they knew he was studying in the seminary incognito. He wrote poems and he saw a lot of tragic events, some tragic events there in the marble quarries because of course safety was compromised by the regime. And so they would blast off a whole side of a mountain and sometimes the marble would catch, huge chunks of marble would catch some people and they would break their hands and so forth. But then also the sculpting of the marble, right? And it says, it is not the hand that strikes the marble. It is the mind that moves the hand that strikes the marble, okay? And so ultimately we take it to the will. And the surgeon doing a salpingostomy necessarily has to will the death of that embryo. Whereas the one doing a salpingectomy does not desire the death of the embryo, but can foresee certainly that the embryo will die, tragically will die, okay? And so it's the difference between killing or allowing to die. It is the difference between killing or allowing to die. Subtle, but very real. We'll pick up this difference again when we get into end-of-life issues in about 3 weeks or 4 weeks, and particularly with physician-assisted suicide, okay? The distinction, fundamental distinction between killing or allowing to die. Basic fundamental distinction in bioethics. Many people don't make it, that distinction. They don't see it, they don't understand it, they don't like to understand it, it's inconvenient. It's one of those inconvenient truths of principal bioethics. Is it making more sense?
It is, it's just, I have a hard time understanding the fact that the woman at this point in time loses the ability, well, not loses, but her chances of having a child are decreased drastically
Yes,
performing one surgery versus the other.
right, of course. Okay, well, let's stay on that for a while, all right? It's reduced. Let's go back to the probabilistic model for a moment. And on average, she loses her opportunity for conception, for having another child, by how much, statistically?
50%.
50% on average, right? We have to say on average 50% because then again, we would, to make a very accurate analysis of that, we would have to see maybe one ovary works better than another and so forth. You know, there are two ovaries and they work kind of independent from each other. Maybe she actually has more mature eggs on one ovary than the other, etc. It's like the kidneys, you know, the two kidneys are not both the same size. One works a little better than the other and so forth. So we would have to factor in all that. But let's stick with a simple split down the middle, 50%. She loses her reproductive ability by 50%. You mentioned drastic. Now, drastic is a qualifier, right? Why is that drastic? You flip a coin, what are the chances of heads and tail? 50%. Is that a drastic loss that I get a tail instead of a head? Is that drastic? Why is 50%? It may or may not be drastic. More important, I would say, is the age of the woman. And typically, ectopic pregnancies can happen later also in life. You know, so there are other factors that are compounded into it. But it's a 50% loss of pregnancy. It's not 100% loss of pregnancy, you know, future pregnancy. It's a 50%. But so she compromised on the possibility of getting pregnant again by half, by 50%. And what was the payback for that? What was the benefit of losing 50% of her ability to get pregnant again? What was the benefit? What did she gain? Life. She gained her life. She was on the road to death. She was on her road to massive hemorrhage, right? And so, what if she lost 100% of her ability to have another child? She's still alive. She saved her life. You know, I mean, in other words, is pregnancy necessary? Is it necessary for life to have a child? You know, it's an added value. That's why the reproductive organs, as important as they are, they're not vital organs. They're not vital. We can live without the reproductive organs, right? So they're not vital organs to the individual. We can say that they're vital in the social sense for the next generation. But then we have bumped it up from the individual to the social level. And as long as some people are reproducing or procreating in society, then that next generation is secured. But to the individual, as important as the vital, as reproductive organs are, they're not vital. Like the eyes and any other, and the hands and the feet and so forth, very important, but not vital. So in other words, reproduction for this woman, procreation, is not a vital function, but her life is a vital function, her very life. And so we have to be sure, that's where the proportionality comes in. Where is it? It's, yeah, number 4. The proportionate great reason. You know, in other words, we're not doing that saphenectomy to cure her acne or something like that, okay? No, it is a matter of life or death. Really, literally, clinically, medically, it's a matter of life or death. Because the pregnancy sadly did not resolve on its own. And that's why it's a shift. You know, it's a shift that many people in society, and you'll talk to people, you'll talk to doctors about this, and oh, you're out of your mind. I will never do a saphenectomy, you know, because my patient is primary. Part of it is because we have already almost half a century of a legalized abortion mentality. If it's legal, you know, why is it so unethical? If it's legal for almost 50 years, how can it be so bad? That's the tidal wave that we're fighting against. It's just ingrained in the culture. A little bit like also the contraceptive mentality. By default, don't have children. And by exception, maybe have a few, but be careful because you're contributing to global warming and everything else. You know, their mentalities, their ideologies that have filtered in big time. It's the truth, okay? I have not said one word about God, faith, or religion here. Just exposing biological, medical, clinical facts. But many doctors will go this salpingostomy. In the case of medication, right. Okay, so we have this other method, textrate, yeah, method. Okay, Chris, I don't know if you have a follow-up or we need to think about this a little bit more, maybe.
Yeah, it's more so something I believe I have to think about a bit more, but I understand exactly where you're coming from, and
The reasoning.
the intent really the intent and the action is really what makes it justifiable and
It bumps it
justifiable.
up. It bumps it up. And, you know, like I say, I present these things all over the place and I say, look, in this whole hour, I have not mentioned once God, faith, and religion. But it's more than obvious that there's a background here. And the background is Judeo-Christian, okay? So when we take the example of Jesus Christ, what he did with the commandments are pre-Christian, right? Because they were given by God to Moses for the people. And that was maybe 1,000 years. We don't know exactly when that happened, maybe 1,000 years before the time of Christ. Certainly the commandments are in the Jewish tradition. It's a summary of the law of the Torah, okay? And, but then, so Jesus as a Jew inherits the commandments, you know, and lives them, but he bumps them up a notch, like that chef says, bump it up a notch. He takes the commandments to a different level. He spiritualizes the commandment. He takes them precisely at the level of intention. And he focuses, because I've been doing some talks on theology of the body by St. John Paul II, and he mentions the sixth commandment. It's all about human sexuality and or masculinity and femininity. It's his anthropology of the human person. So when we look at what Jesus did with the sixth commandment, with the commandments in general, but particularly the sixth commandment, it's a big bang, you know. What happens? It's in the context of the Sermon of the Mount, and he's taking the commandments and he's Christianizing them, all right? He is taking them at the level of spirituality, of the intention, of the conscience. He says, you have heard it say, do not murder. But I say to you, if you think ill of someone else, you have already murdered that person in your heart, the heart being the conscience. See, think ill. So I haven't even touched the other person. The other person has no clue that I hate their guts. For example, when I'm driving and people go crazy around me, you know, I have already killed those people. I have committed murder in my heart, in my soul. That's pretty grave. Then he takes the sixth commandment. You have heard it say, do not commit adultery. They're talking about the actual physical act on the ground, okay, between two people who are not married. The actual physical act, that's do not commit adultery. But I say to you, if you have thought, if you have lusted basically with another person, okay, if you had desired another person who is not your spouse, you have already committed adultery with her in your heart. I haven't touched the other person. The other person doesn't know that I have lusted. And I have already committed that adultery in my heart. That's a very high standard. That's the Christian standard because he takes it to the level of intention. Wow. So is that challenging? You know, I think it was C.S. Lewis who would say, it's not that Christianity has been tried and failed. It's that Christianity has never really been tried fully, you know, because it's so challenging, it's a work in progress. And that's also why in the Catholic Church, we have confessions so that we can repent from the evil intentions and start afresh, okay, with God's grace and God's mercy, because he knows, the Lord knows. that at the level of the intention, we're going to fall. And nobody knows except two people. Because nobody really knows what I'm thinking about right now. In the core of my being, no one really knows what I'm thinking about except two people, God and myself. Okay? And that's the challenge. The challenge is to take it to the level of the intention, but it truly really highlights it. So in principal ethics, we're always looking at the intention as the means. What are the means that are being used? The intentions have to be clean and pure. Otherwise, we call it they vitiate, they contaminate the act. You know, an act that could be in principle be good, for example, giving alms. All right, so giving charity. All right, I'm giving charity, but guess what? I'm giving charity because if I earned so much money last time, this past year, that if I don't give charity, then my tax bracket is going to be higher. So I'm really giving charity so I don't pay as many taxes. So what's the intention? Is it because I care about the underprivileged and the ones who need the charity? I couldn't care less about those people. You know, I just want to lower my tax bracket. So I just contaminated my good act of giving charity. It's still charity. I'll still get the letter of the nonprofit organization to deduct the charity. But that act was actually for the wrong intention. Now, if it's a side benefit that I get a tax benefit out of it, praise be to God. And here's the proof. Would I do the same charity if I didn't get the tax benefit? Yes or no? That tells you really what my intention is. If I would do the same charity without getting the tax benefit, that is kind of the proof of where my intention is. Some would and some wouldn't. And then that determines really what the real intention was. You know, now, if it's an added benefit, praise be to God. That's the thing with NFP, all right? When it's used specially to avoid the children, all right? We want to avoid the children because of the serious reasons, right? The grave reasons. But if we happen to get pregnant, as hard as we try to determine that ovulation, we still get pregnant, well, we're not going to kill the child. We're going to accept that pregnancy. We're going to accept the child. Right? That's, so the intention always has to be in the right place. And it's very challenging in our society that is moving, is galloping in a different direction. In a utilitarian, if it works, do it, just do it, do it, do it. And move forward. No time to lose. So, all right, let's look a little bit at this methotrexate. Methotrexate. If I divide the word into two parts, I can almost say it. Methotrexate. Okay. This basically is a replication inhibitor. All right? It's a chemical substance. Typically is used in cancer treatment. Why? It's a inhibitor of replication. Now, remember mitosis, good old mitosis, your ptosis, everybody's ptosis, the stages of mitosis and so forth, the cell cycle. What happens at the end of interphase just before, from here to here? What happens at the end of interphase? Yeah. Maybe I get lucky. It's down here somewhere. Yeah. Patience will get us there. I saw it. I saw it. I did see it. Yeah. Where's gap one? There we go. Okay. Remember DNA synthesis, the S phase in the cell cycle? all right? DNA synthesis. It's another word for replication. And another word for replication is duplication, right? That needs to happen in mitosis. I only have two options here with the Zoom, sorry. Bigger or smaller, let me see. What is replication? What is duplication? Okay. Remember what happens with duplication. What is duplicated? What is replicated? What is the synthesis? DNA. Remember, is duplicated, so temporarily in that replication, in that DNA synthesis, our cells will have 92 chromosomes temporarily, so that when the two daughter cells split, each one will end up with 46 chromosomes, or 23 pairs. Remember, so temporarily there is a duplication. They don't actually show it. They show the DNA duplicates, all right? So that's replication. Cellular replication is at the last phase, synthesis before GAP2. GAP2 is the second checkpoint to make sure that everything is replicated, and then it goes, the cell goes into mitosis, all right? The chromosomes go to the equator, and then they split and they go to either pole. My point is that methotrexate inhibits DNA synthesis, inhibits replication. So if there is no replication, what happens at GAP2? It doesn't pass the gap. It doesn't pass the gate. The mechanism of GAP2 says, no, you're not ready to replicate. You're not ready to split into two cells. This cell, I'm not ready to split into two cells because the DNA has not replicated, okay? And so what happens? It stops cell growth. And that's why it is a cancer inhibitor, because it stops cell growth. And what is cancer? By definition, cancer is uncontrolled growth of the cells. The cell goes crazy here, keeps reproducing, keeps duplicating and forming a tumor, a mass, right? Then when that mass starts migrating, when those cells migrate to other places, that's metastasis, that tumor is malignant. All right, so methotrexate is very good in that sense that it inhibits DNA synthesis, it inhibits replication. So in the bigger picture, it inhibits the cell from duplicating, from mitosis. It's a mitotic inhibitor, all right? Okay, so keep in mind, a mitotic inhibitor. The case of cancer, it's a good thing. In the case of the ectopic pregnancy, or any pregnancy, excuse me, let me get a diagram here. All right, so it's going to inhibit, that methotrexate is going to inhibit cell growth, right? Now, for the woman, it's going to inhibit the cell growth of the woman, but it's also going to inhibit the cell growth of the embryo growing within her. It's all in the doses, because the woman has trillions and trillions of cells. And the organs are made up of millions or billions of cells. So if some of those cells are inhibited in cell growth, who cares? She still has other growth, other cells that are still growing, and the tissue is being replaced, or the tissue may not grow as fast or replaced as fast during the treatment, during the protocol of the methotrexate, okay? But if there's an embryo who's growing there, and that embryo is receiving methotrexate by biomass, just consider the biomass, all right? The bulk tissue mass of the embryo of a blastocyst or a gastrula in comparison to the biomass of the mother, of the body of the mother. Much smaller biomass, right? So the dosage is going to have much more impact of methotrexate. It's going to have more impact on the embryo than on the tissue of the mother or the whole body of the mother. So what's going to happen? That methotrexate is going to inhibit cell growth. It's going to inhibit the embryo from growing, but more importantly, it's going to target, because methotrexate targets actively growing cells, cells that are actively growing. Okay, now, for biological purposes, for the purpose of argument, this embryo, which is going to lose some resolution, it's kind of simplistic, all right? But at least this little embryo has an umbilical cord. And what is on this side of that umbilical cord? On the outer layer, on the trophoblast? What is forming there? The trophoblast becomes the placenta. Come on, in your sleep. All right, so here's the embryo proper, came from the inner cell mass. We're going to talk about the inner cell mass now in stem cell research. And the trophoblast will begin forming the placenta. Methotrexate, you need to know, targets actively dividing cells. Cells that are actively growing and dividing is tissue that is growing fast and expanding. Which is the tissue that is growing fastest and expanding in this blastocyst, in this gastrula? Proportionately, which is growing faster, the actual embryo, who's actually enclosed in these membranes, or the trophoblast, beginning to form the placenta, very actively invading the tissue of the mother, whatever tissue that is, all right? Bottom line, the placenta, the trophoblast, is the tissue that is growing fastest here. It's a tissue that is growing faster because the embryo drastically depends on that connection. Now that there's a beginning of an umbilical cord, all of the nutrients are going to come from that placenta, and also getting rid of waste products and so forth, right? Especially CO2. And therefore, the placenta, the trophoblast, is the one that's growing active. Methotrexate is going to target that tissue, and is going to inhibit cell growth. It's going to inhibit mitosis of the trophoblast. It's going to inhibit the establishment of the placenta. Now you could say, well, that's a good thing, right? Because the placenta is precisely what is threatening the life of the mother by threatening to burst to cause a massive hemorrhage. So you could think at first blush, methotrexate, good thing, is targeting the placenta. However, what is the placenta to the embryo? Is it similar to the hand, my hand, or is it similar to my heart? Yes, to the heart. Can I do without my hand and keep on living? Yeah, I'll miss it, but I can do without the hand. I can do without the whole arm. I can do without both arms and both legs. Can I do without my heart and keep on living? Not. So we're talking about a vital organ. Bottom line, the placenta is a vital organ to the embryo. But the placenta is discarded upon birth. Yes, it's a temporary vital organ. But it's a vital organ. It's a vital organ to the embryo. So when I target a vital organ, it is equivalent to putting, an overdose of potassium chloride to my heart, which will cause a heart attack. All right? And so I'm targeting, when I give methotrexate to a pregnant mother, I'm targeting the vital organ of that embryo or fetus, which is the placenta. Okay? So I'm intending to kill the placenta, therefore to kill the fetus. Again, oh no, I'm not killing the person. My hand is just injecting potassium chloride into this 4-chamber pump that the person has in the middle of their chest. Yeah. So giving methotrexate to a pregnant mom is killing the embryo. Okay? And we cannot but desire to kill the embryo when we target the vital organ, the big vital organ at that point, which is the early placenta, the establishment of the placenta. You follow? And in other words, so the good end, oh, and this one has even more appeal. So some doctors don't even do the expectant thing and wait for the 90% resolution. Right away, they give methotrexate. Because clinically, you can see the advantages. Clinically, there's no surgery. It's a medical procedure. It's non-invasive in that sense. Takes care of the early embryo. So we're talking about the blastocyst or the gastrula as soon as he or she is discovered, all right? Without letting the body self-resolve. We jump the gun in a sense and resolve it ourselves with the methotrexate. And then of course, once that embryo dies, that blastocyst or gastrula dies for lack of nourishment from the trophoblast, from now the dead trophoblast, okay, then the body will certainly discard that or reabsorb that tissue there. You follow? So methotrexate is even more appealing. There's no scarring and so on and so forth. So it has all of the advantages of taking care of the ectopic pregnancy and none of the disadvantages of the salpingostommy. So it's even more appealing. But frankly, an honest doctor, an honest OB-GYN could not prescribe methotrexate for an ectopic pregnancy without intending to kill the embryo, because he or she, the doctor, is intending to inhibit the establishment of the placenta, which is a vital organ for the embryo. Follow? So that's the logical reasoning all the way through. Very biological, very medical, very clinical. No faith involved here. But the underlying principle is that that blastocyst is as human as the rest of us. Okay? So that's methotrexate. Most popular today for ectopic pregnancies.
I have a really quick question on that.
Yep.
So would that be a utilitarian view or a principle view? It would be utilitarian because
Exactly.
you're killing the embryo directly by not allowing it to get its nourishment from the placenta.
Right. Yes, exactly. And again, you just said by not allowing its nourishment.
I apologize.
I know. It's habit, you know, we just brush our teeth automatically. So yes, exactly. So think about this. Why is it utilitarian? We can generalize. So we go from the particular to the general in philosophy. How do we do that? Well, the general principle is that the end justifies the means. And that's the bottom line, the bottom line difference between utilitarian and principled is that in utilitarian, the end justifies the means. The end is actually excellent, is clinically, you know, primo. But the means, there's a detail that we're going after the embryo directly. That's the means, right? And because it's legal, because the utilitarian will say, don't break the law, don't break the law, don't break the law. It's legal, so why not? It's clinically better for the woman. The principal person will say, you know what? The means have to be justified in themselves. The means have to be justified in themselves. The end is excellent, but the means have to be justified in themselves. You know?
I have a follow-up question.
Yes.
With salpingectomy, you're indirectly, well, okay, you're removing the tube of the woman, so she is no longer allowed to receive the nutrients from the woman. So how is that different than using methotrexate?
Yes, it's different in the sense, I have not really touched the embryo. I have not touched the embryo. I can foresee certainly that the embryo will die. There's absolute certainty that that embryo will die unless we attempt reimplantation, right? Okay, so we bracket that embryo will die, but I have not touched the embryo. It is tragic, I will mourn, okay? But what I'm addressing, Chris, basically I'm addressing this gray part, all right? The pathology, that's what I'm addressing. I'm addressing this pathology that is a clear and present threat to the life of the mother, not even just her health, but her very life. Also with the background that this tube, and in fact, this whole reproductive organ is not necessary for my patient to live. So I could, me, surgeon, potentially remove the entire reproductive system and my patient will live because I have a pathology. So even the cancerous uterus, the cancerous pregnant uterus is even more drastic because I'm removing the whole reproductive system. And that's 100% sterilization, but it's therapeutic. It's not non-therapeutic. It's therapeutic sterilization. And there is an embryo there, okay, or a fetus. But again, double effect. So in the cancerous uterus that is pregnant, it's even more drastic because there she loses 100% of her fertility and she saves her life. All right. Again, she can be heroic and say, I bypass therapy and I pass the hysterectomy and so forth to give life to my child. It depends a lot on how advanced the fetus is, how advanced the pregnancy, because if the cancer is very close to the fetus, the cancer may actually invade the fetus and it's futile. You're not going to save either the mother or the fetus, all right, by bypassing the cancer therapy. But if the cancer is, like say, in the ovaries as opposed to the womb, then it's possible to give enough time for the fetus to become viable and then perhaps do a C-section. And then maybe the mother could still be in time for the thing. But anyway, I've diverted from the question. Yes, we're not intervening directly on the human being. Okay, we're not intervening directly. I understand perfectly, but you see, the tube is not going to be the proper place for, we know that the tube will not be able to sustain a placenta. Going forward, you know, we can push with our mind's eye, we can push this pregnancy forward within days, not even weeks. That tube is not going to be able to sustain a pregnancy. It's going to stretch out, it's going to become thin, paper thin, and then it's going to explode, and it's highly vascularized. And now I have massive hemorrhage on my patient because I didn't take care of a pathology early on, all right, when the tube was just becoming inflamed. And so it's tragic, but that embryo is just at the wrong place. At the wrong place. And because the body did not take care of that pathology, now clinically, we need to take care of the pathology. But there's a way of taking care of the pathology without intervening directly on the embryo. It makes a difference. It makes a philosophical difference and it makes a bioethical difference. Again, if in the future, it will become like a standard procedure, standard protocol to be able to reimplant this embryo, then that would ethically obligate. Following the sapingectomy, the surgeon would be obligated to implant. But and that's still an experimental procedure. The problem is, it's a catch-22. How do you standardize that procedure? Clinically, a procedure is standardized. How does a clinical procedure, how does a medical procedure go from experimental to clinical? With trials and errors and standardization. So how are the trials? We're back to experimenting, and we cannot justify experimenting with the human embryo, risking his or her life. You see, so it's in a quandary. We're caught in a catch-22. We can experiment with mammals, and we can generate an ectopic pregnancy in a mouse. You know, that can be generated in the lab, and then try to reimplant that ectopic pregnancy in the mouse womb. So that becomes a model, an experimental model. And if we do that enough times and see what is the proper way to doing that, let's say once we excise the tube, for example, should the tube be split and spliced open and then the embryo placed against the endometrium of the mouse, or where should we split? I mean, I'm just thinking out loud here. Logic would say that if we're going to splice open that tube, very carefully maintaining the integrity of the embryo, because we're talking about a microscopic being here, right? The mouse, the microscopic embryonic mouse, it stands to reason to splice on this side so that the placenta has a chance, the trophoblast has a chance now to invade the actual endometrium of the mouse uterus. You follow the clinical logic here and so forth, but that's highly risky. You know, what kind of, we're talking microscopic, how we're going to split that and slice it and so forth. Maybe sew it there so that it stays in place enough time to generate the placenta. going forward, what effect does it have on the mouse to have that piece of tissue of the tube on its back as the mouse embryo grows? Will it cause abnormalities or not? All that would have to be studied in luxury of detail, right? Before we would attempt it on the human. And then the mouse is a mammal, but it's not a primate. So we would have to scale it up to the primate. Now we're talking about possibly chimpanzees doing this. And how humane is that on the chimpanzee? You know, because how often, if 90% of these resolve spontaneously, and if there's already a procedure to save the life of the mother, does it justify putting chimpanzees, galore chimpanzees, through this whole process just to experiment on reimplantation of ectopic pregnancies so that one day maybe we can develop a protocol for the human when 90% of them resolve spontaneously and the other 10% can be taken care of by sapropingectomy. You follow me? So where's the humane justification of choosing chimpanzees? In fact, the medical profession is trying to get away from using primates altogether in clinical trials before jumping to the human. It's challenging. You follow? So there we are. Back to but thanks be to God, we have the principle of double effect. If we understand the principle of double effect, it is stellar to be used specifically in clinical practice, in medical practice, okay? Because it really applies. It applies even more drastically to the cancerous uterus that is pregnant, all right? Double effect, double effect. Important to review it, to consider each point. Again, the one act simultaneously has two effects. What is the one act? The one act is the ectopic pregnancy and how to resolve that ectopic pregnancy that did not resolve by itself, okay? Sapropingectomy or salpingostomy or methotrexate. Simultaneously, a good and a bad can come out, then the steps to justify double effect. All 5 conditions must be fulfilled, all right? Okay, so now we can talk a little bit about today's lecture, which is stem cell research and human cloning. A little bit of a follow-up, but you see now we have more interventions, more human interventions on beginning of life issues on the human embryo, all right? And so are they justified bioethically or not from the principal perspective? We know that from the utilitarian perspective, there's a lot of good to be gained from these procedures, but are the procedures in themselves dignified or not? Do they respect the dignity of the human embryo? Okay, so let's see. We got stem cell research, and then we got cloning. So it's almost 11. How do you feel? You want to break or you want to continue a little bit? Break? Okay, good. Break to thaw out, especially here where it's 50 degrees outside and it's 40 degrees inside. So we're going to go outside to thaw out a little bit. Come back in about 5 minutes. Is that good? Okay, come back at 11:05, more or less, 7 minutes. All right, very good. Let me pause and we'll be back in a few minutes. Thank you. Okay, welcome back. The second part is actually, I think it's gonna go a little faster because it's kind of a review of what a lot of what we've been covering before, and then the application either into stem cell research or into human cloning, okay? So we're going to look at what is stem cell research, and then the distinction between human and non-human stem cell research, the distinction between adult and embryonic stem cell research, and then some other types of stem cell research, cord blood, iPSC, induced pluripotent cells. And then this is cloning here, A fancy word for cloning is somatic cell nuclear transfer, or SCNT. Sometimes you just see NT for short, nuclear transfer. And then the distinction between reproductive and therapeutic cloning. So let's go forward. All right, with regards to stem cell research, right, I asked the initial question, just at first blush, would you say that the Catholic Church is in favor or against stem cell research? How many of you would say that the Church is in favor of stem cell research? Or against stem cell research? Or unsure? Exactly, it depends. Exactly. So we have to make distinctions, all right? I can tell you, if the question is just asked like that, is the Catholic Church in favor or against stem cell research? My answer is that not only is the Catholic Church not against stem cell research, the Catholic Church is actually involved in stem cell research. But then, of what kind, you see? Because we are not about killing human embryos either. So we have to make distinctions. And at least two levels of distinction, all right? Two levels of distinction is, reminds me of a little saying that is attributed to Thomas Aquinas, again, the great systematizer of Catholic theology and morality. He would say, at least attributed to him, he would say what? Never affirm, seldom, no, he would say never negate, seldom assert or affirm, never negate, seldom affirm, and always distinguish, always make distinction. Okay, so the first level of distinction is between human and non-human stem cell research. In other words, when we talk about stem cell research, people just assume that we talk about human stem cell research, but not necessarily. I can be talking about non-human stem cell research. For example, in mice, right? In mice, in laboratory animal experiments, in models, which typically are mammals, and the mammal that typically gets it in the lab is the mouse. So that would be non-human stem cell research, okay? So that's the first level of distinction. We may justify ethically some non-human stem cell research that we would not justify on the human. But then that's necessary, that first level of distinction, but not sufficient. There's a second level of distinction that we also need to make. So now we're talking about human stem cell research. Notice the adjective. Okay, so it's clear that we're talking about human stem cell research. The second level is, well, are we talking about embryonic stem cell or adult stem cell research, right? And that's precisely the ethical question here. And so when I mentioned that the Catholic Church is actually involved in stem cell research, obviously it is adult stem cell research, which does not involve the killing of human embryos. So the reason why the Church is against human embryonic stem cell research is because it kills the embryo, all right? So what is stem cell research? Or the question is, where do the stem cells come from? That's the whole thing. These stem cells, right, are actually pluripotent cells. They're pluripotent. And where are the pluripotent cells? In the inner cell mass, the ICM. So remember the diagram or the structure of the blastocyst, right? The third stage of embryonic development. We got zygote, we got morula, and then we have blastocyst. Remember that the zygote is totipotent because it's a single cell, and all the potential to become a human or whatever species is contained within the zygote at the genetic level, obviously. Then the morula, each blastomere, each cell of the morula is also totipotent. That's the next diagram that I have there. But by the time we get to the blastocyst, now we have cellular differentiation. We have the first level of cellular differentiation. In other words, we have two types of cells, two types of tissues that are different from each other. That's cellular differentiation, two types of tissues. The tissue on the outside of the blastocyst that forms the actual ball, right? The sphere, that is known as the trophoblast, the outer layer. And then the inner layer of cells, which is different genetically or in the expression of those genes, that is what is known as the inner cell mass. The inner cell mass, just very unimaginatively, it's a mass of cells that is growing inside. It's not a tumor, it's an inner cell mass, the ICM. And I've mentioned several times that the embryo proper comes from the ICM. In other words, the ICM is what continues to develop into the embryo. For example, during gastrulation, what gastrulates is the ICM into what is known as a gastrula. The gastrula now begins to elongate and establish a head to tail region, and also bilateral, so either side of the groove or the neural groove and so forth. That's the gastrula, which is the next stage after the blastocyst, okay? That gastrula properly comes from the ICM, we understand. And then the trophoblast, of course, becomes the placenta. You can think of it again functionally. What is in contact with the endometrium, it will be the blastocyst, right? In direct contact. Remember, there's that hatching, the little film that I show you, where the embryo sheds, the blastocyst sheds, leaves behind the cumulus of the corona radiata and the zona pellucida, right? Sheds, comes out of that cumulus, and then that little embryo will implant himself or herself into the endometrium if everything goes well. All right, so it's the ICM that is the stem cells. The ICM is the stem cells. So you see, to obtain these embryonic stem cells, this embryo needs to be teased open, needs to be disaggregated, lose its integrity, his or her integrity, right? And to pull out that ICM, I need to get literally inside the embryo and pull out the ICM and put that cluster of cells onto a Petri dish with nutrient environment that is conducive for cell growth, and develop a cell line, right? Develop confluence. In other words, that ICM will continue to grow, all right, unrestricted until that tissue now hits the edge of the Petri dish, and that's called confluence. And then that tissue needs to be passed on to another Petri dish, otherwise it overgrows. Actually, if the tissue is normal, when that tissue hits the border of the Petri dish, typically it stops, it inhibits itself because they've hit a boundary, all right? But then those cells are gonna get old, so they need to be passed to, some of the tissue needs to be passed to another Petri dish, and that's called passage. And it's in the passage that the cell, that tissue eventually becomes immortalized. Immortalized meaning that it continues to grow, in principle, indefinitely, all right, in the passage. So confluence leads to passage, continuous passage, iterated passage may lead to immortalization of a cell line. We have in the body about 200 different cell lines that make up all of the organs and tissues of the body, about 220 cell lines. And the idea originally, when all this started back in the 90s and thereabouts, was to develop enough cell lines to be able to make up for the 220 cell lines of the human body, so that eventually we could replace any organ or tissue with these embryonic stem cell lines that have been developed in different labs of the world, okay? So that was the idea behind embryonic stem cell research, if you will. It was a good idea. It was a noble end. It was a noble end, in other words, with this type of regenerative medicine. It's called regenerative medicine. In principle, theoretically, any organ or tissue of the body would be able to be regenerated, okay, by the cell line, by the precursor cell line that would be stored in a lab, ready to be used when the tissue or organ became pathological. So that was the whole theory behind it, very, let's say, good, noble theoretical end. But it happens that the means of obtaining those embryonic stem cells is to kill the human embryo. Because when I disaggregate a blastocyst, in fact, I am killing the embryo. Okay, and I cannot disaggregate a human embryo without desiring to get into the ICM. And desiring to get into the ICM and to pluck the ICM out is, in fact, killing the embryo. All right, so we have to be careful not to be schizophrenic here and be of logical consistency. I need to desire the killing of the embryo to get that ICM. Now, let's look a little bit at potency so that we are clear on that, because cell potency is essential. This is a one-way road, and this is essential to happen in all living organisms in order to develop differentiated tissues. Now, most of the tissues in our body are differentiated, okay? The organs are differentiated so that the liver does not do what the brain does, and the heart does not do what the kidney does, and so on and so forth. Our organs and tissues are differentiated into particular functions. Again, form follows function. The structure of the thing is according to the function of the thing. And so the vast majority of the tissue in our body is differentiated, okay? But we have some undifferentiated tissue or partially undifferentiated. Those are germ lines that are there, and they are involved in repair mechanism. When there's an accident or an injury, and some of the tissues, some of the organs have regeneration power, all right? That's because of their potency. So we start with totipotent. Again, the added value of the course, a little Greek and Latin. Toti is a reference to the total, right? Full potential to develop into a full organism of whatever species. So in the case of the human, here is a zygote, and we see this, these are photographs, by the way, micrographs, all right? We see the two pronuclea beginning to fuse here, so syngamy has not completed yet. We also see the two little polar bodies stuck in here in the zona pellucida, right? Etc. But this is a zygote, and this zygote, a single cell, new individual in the process of completing syngamy is totipotent because we only have that one cell, and the whole organism will come from here. So that's totipotent. But the morula also, I've mentioned several times that each blastomere of the morula is also totipotent. And these were experiments done by Hans Spemann a century ago, a German fellow who was working with frogs, amphibian embryos, and precisely disaggregating the morula. And he noticed that if he disaggregated the morula and freed up the blastomeres individually, that he would get little frogs from each blastomere, right? He would get clones. And so what he would do is he would compromise the integrity of the morula, essentially get rid of the corona and so forth, and then just let the blastomeres individually float around in a nutrient medium. And he would essentially, these blastomeres kind of reverted to the zygote stage. Each blastomere then generated a morula in itself, okay, with amphibians, with frog embryos. And those morulas eventually develop into blastomeres, develop into blastulas, and then the blastulas continued into gastrulas and so forth and develop into little tiny tadpoles. So the bottom line is that the blastomeres of the morula, the individual cells, are also totipotent. No cellular differentiation yet. The third stage, the blastocysts, yes, I already covered that. So they are no longer totipotent. Individual cells of the blastocyst are no longer totipotent. Now they are pluripotent, meaning that they can become many cells of the body, many tissues of the body, but not all the tissues. And in fact, the big dividing line is there between the embryo proper and the placenta. So that the trophoblast will become the placenta, and not the actual embryo proper. And the embryo, the ICM, will not become the placenta. The ICM will become the embryo proper, okay? And so I have a diagram here. This is a photograph, micrograph of a blastocyst. And then this is a cross-section diagram of a gastrula. Gastrulation going on where we have the three germ layers of ectoderm, mesoderm, and endoderm, right? All of the organs and tissues will come from these three layers, and that's why they're called germ layers. They're germ layers, they're pluripotent, all right? So they have a lot of potential, but they're not totipotent. And so many organs and tissues will come out of the ectoderm, and other organs and tissues will come from the mesoderm, and other organs and tissues will come from the endoderm, but they are distinct from each other, right? For example, you're going to get typically from the ectoderm, you're going to get the skin and the nervous system. From the endoderm, typically you're going to get internal organs and tissues, the internal, like the digestive system and the respiratory system, some of the very internal organs of the core. And then the mesoderm is going to be mostly bone and muscle. But then there's some mixture of these layers also. But the point is that you get distinct organs and tissues from each one of these three layers. And therefore, they have lost their totipotency and they are now pluripotent. Pluri meaning many, but not all, all right? As differentiation continues during pregnancy, in the fetal stage, after basically up to the second month, the 8th week, when we have all of the major organs and systems in the miniature embryo, all right? As that differentiation continues, then the cells pass from being pluripotent to being multipotent. So multipotent is differentiation within systems. So for example, the respiratory system involves, starting from the neck down, well, it involves actually the mouth, it involves the trachea, it involves the lungs, it involves the alveoli and so forth. So all those different organs and tissues developing, that is pluripotency, that's multipotency within the one system of the respiratory system. We can make the same argument for the circulatory system. Circulatory system involves the heart, involves arteries and veins, involves capillaries, et cetera, all those tissues and then are multipotent because they're becoming more and more specialized. And then finally, the fourth stage of cellular differentiation, the fourth stage is the final stage, fully differentiated cells, okay? Fully differentiated cells, tissues, and organs, like we have in our body, the vast majority of them that are doing their function and no other function. That's fully differentiated. Normally, naturally, in nature, this is a one-way street. This is one way from totipotent at the zygote level to fully differentiated by the time that animal either hatches or is born, and implants the same argument, okay? In fact, even in mushrooms, in the fungi. So those are all the multicellular groups. It's one way from totipotent after fertilization to fully differentiated when we have a functional organism, right? One way. Now, what happens with stem cell research is that with the embryonic stem cells, they try to go backwards on the process. In other words, with pluripotent cells, the ICM, go back to regenerate tissues or use up the pluripotency of that ICM, okay? But it is an artificial way because natural, normal blastocysts don't naturally disaggregate and have the ICM live by itself, all right? It has to be with the full structure of the ICM and the trophoblast. So this really doesn't happen in nature. Again, the bottom line, as you can see, is that we are against embryonic, human embryonic stem cell research because it goes after the ICM, in effect, killing the human embryo, all right? So necessarily today, in order to obtain human embryonic stem cells, human embryos need to be killed, all right? If in the future, some kind of a futuristic medicine, one was able to pluck out 1 or 2 cells from the ICM and develop those cells into confluence and passage and immortalize them into a cell line in a lab, well, perhaps we could justify it if it did not damage, if that procedure did not damage the blastocysts. But think about it, you know, the level of sophistication needed to pluck out 1 or 2 cells from the ICM without doing damage to the embryo as a whole. It would be a very, very sophisticated technology, very expensive, number one. Number two, we don't even know what kind of damage we're doing to the ICM by removing cells there, because it's different from removing totipotent cells from a blastomere, from a morula, okay? We know that the morula minus 1 blastomere can still develop into a normal morula because it's been done experimentally. But for the ICM, we don't know if plucking even just 1 or 2 of these cells will damage that embryo significantly. We may be removing part of the body, all right? Because already these cells are no longer totipotent, they're pluripotent. So we just don't know. And therefore, we gotta leave the embryo alone. We gotta leave the human embryo alone if we're gonna be consequential. However, the beauty of it is that we have adult stem cells. We all have stem cells in our bodies that are involved in regenerating tissue. For example, if I cut myself, that cut is going to heal from the inside out with new tissue. Where did that tissue come from? That tissue came from stem cells that are embedded in the dermis or even further down into the adipose layer. What's another name for the adipose layer, adipose tissue? Fat tissue. In the fat, we have stem cells that are embedded in there and are just waiting to be stimulated into regenerating the tissue wherever they are, okay? And so those are multipotent stem cells. They're not pluripotent, they're multipotent because they're in different organs and tissues of our body, okay? They are adult simply because they're from the born. So even babies, a newborn baby, technically has adult stem cells because now they're born. You know, we're not going after the ICM. So embryonic stem cells come from the ICM, but stem cells in a newborn baby, technically they're adult stem cells because the baby's already born, all right? And we're not going after the ICM. So follow, that has philosophical and bioethical implications. So from the newborn forward, we all have adult stem cells. They're not pluripotent, they're multipotent, which is actually a better thing, biological. I'll explain it in a minute. Is there an ethical issue with using adult stem cells? Well, there is one ethical issue, but it's certainly not killing the embryo, right? So what is the ethical issue? The only ethical issue is consent, that the donor needs to consent to donating their stem cells. Okay, so when it's an adult, a legal adult, you know, a chronological adult, 18 years old or earlier or later in this country, then the adult consents. If the donor is a minor, the parents consent, all right? So even of a newborn, conceivably, if it's going to help save the life of another sibling or something like that, then the parents could consent, because obtaining his stem cells, so we have stem cells kind of all over the place, and they're being discovered little by little, more and more. So for example, the pulp of baby teeth, you know how we shed our teeth? Well, the pulp of baby teeth has stem cells in it. Hair follicles, that's why we regrow hair when we pull it out. Not over the long run, we kind of lose those follicles, okay? I'm a witness to that, but younger, the hair follicle actually has stem cells there. Stem cells, like I mentioned, in the adipose tissue. Even now in the circulatory system, they found stem cells in the blood itself that are just wandering around waiting to be used, all right? So for example, just an equivalent to pheresis. can obtain stem cells. I don't know if you people ever done phoresis. Phoresis is a type of blood donation, but instead of being RBCs or whole blood that we're donating, actually we're donating platelets, all right, which is another component of the blood. What are called the corpuscles of the blood, or the tissue component of the blood. Remember, blood is a liquid organ, right? And blood has significantly red blood cells, white blood cells, and platelets. The platelets are involved in the scab, in the healing process, all right? And so people who are hemophilic, for example, they don't produce platelets or enough platelets, and they have a problem in the production of platelets. So stem cells, platelets are collected from blood. It's more extensive than just a blood donation. A blood donation, what is it, a pint or something like that, is done in 5, 10, 15, 20 minutes. But a platelet donation may take a couple of hours, and they hook you up to a machine similar to pheresis. It's called pheresis. It's similar to a kidney, what's it called, dialysis, whereby they take out the blood from one vein and they put it through the machine, and the machine filters out. In the case of kidney dialysis, they filter out the waste product of the toxins in the blood. In the case of pheresis, they filter out the platelets from the blood, and then they pump the blood back in through the other arm. And that's done in a very cold machine. So the pumping back is cold blood, and one gets very cold. So we keep putting blankets on top of you to keep you warm after several hours, how long that you can resist the cold internal weather circulating. Anyway, long and the short is that pheresis is now a standard procedure for collecting platelets. Well, a similar, analogous to that, could be done for collecting stem cells from the blood, all right? They're not gonna collect as much stem cells, they're fewer, but they can collect enough amount to do a transplant of stem cells, adult stem cells, and all that's required is the consent of the donor, all right? And now, on top of that, that transplant can also be autologous, meaning that is for the same patient. And the big advantage of that, there's no immune rejection. No immune rejection. So keep in mind, for embryonic stem cells, bottom line is they're lousy. Embryonic stem cells, really, theoretically, they're the best because they're using pluripotent cells, which theoretically, in principle, are able to replace every organ and tissue of the body, but in practice, they don't. What happens? When this has been done with these ICMs, the embryonic stem cells have been transplanted in labs, okay? Because to this day, there has not been a clinical trial on humans that has followed through all the way to healing using embryonic stem cells, human embryonic stem cells, okay? Follow the argument. It's been done in labs. Typically, the mouse is the one who gets it, or the rat, because the rat is a little bigger to work with. So what is the scenario with embryonic stem cells in the rat model? What do? Okay, so they take a rat, and typically they take a female whom they have impregnated, all right? And so the embryo of that female, so that at least 50% of the genome is compatible, right, to that rat. So they take that rat female who was impregnated with her egg and the sperm of a male rat. And so 50% of the genome of that embryo is compatible with the mom. Then they take out the blast, or they never actually implant. They do it in the lab, they do it in vitro, and then now they have this embryonic ICM, right? 50% compatible with the donor of the egg. Or I'm just thinking out loud, they can use the male also for that matter, because there's no implantation. All right, so now they take either one of the parents, actually, the mother or the father, and they sever the spinal cord partially. Yes, they surgically cut the spinal cord partially, so that now the rat is either paraplegic or quadriplegic, typically paraplegic. In other words, they have upper body function, but they don't have lower body function. So I mean, it's kind of drastic, it's sad. These are experiments possibly justifiable in medicine for the benefit of future benefit to humans. What does this paraplegic rat look like? Well, it's a rat who basically drags itself through the front legs, all right? Because the hind legs are not working, so they drag their body with the front legs. They're alive. Frankly, I don't know if they're in pain or not, but they are severed and they are paraplegic. Then they proceed, the researchers proceed to inject the ICM, which is now the embryonic stem cells, right? They inject the ICM directly into the site of injury because they're pluripotent, and to see if that injury gets healed, right? And the partially severed spine gets healed because that's the most crucial tissue. Is neuronal tissue, is the one that regenerates the least. And so that's the big target in science, in research. So they inject the ICM of the embryo into the severed spine of the paraplegic rat, and then wait a few days, see what happens. The typical scenario is that not only does the spine not regenerate, the rat actually grows a tumor on her neck or his neck. The rat grows a tumor on its neck. We can call it because not being a person. Anyway, what does that mean? That the pluripotent cells have too much potential. They have too much potency. Precisely because they come from the ICM, the whole embryo wants to grow there. A pluripotent embryo wants to grow there. And so they have too much potential. You see, the pluripotent cells have too much potential, too much biological potential. Better are multipotent because they're toned down. And I just give a simple little analogy. Let's say we have a transistor radio when they were still around, and it takes a 9-volt battery to run the transistor radio, all right? But I have a battery that has 2,000 volts. And it's the same size as the 9-volt battery, but it has 2,000 volts. And I put that battery into the radio, and it's going to frazzle the radio because it has too much potential. You follow? Same size, but it has too much potential. So that's what happens with embryonic stem cells when they were tried in animal trials. At one point, I think it was Geron Corporation. Geron is one of the original biotechs that appeared in California back in the 70s, I think it was. These biotech companies, upstarts that were very promising for the market because they had a potential for benefit in personalized medicine and regenerative medicine and all that. And so Geron finally obtained a permission for a protocol from FDA, Food and Drug Administration, which is the one that regulates this research, the human research and so forth, to do a protocol. And it wasn't even life-saving. It was like, for example, to diminish macular degeneration, okay? Macular degeneration on the eye, so that people who have macular degeneration may become blind. So it's not a life-threatening thing. The worst case scenario of macular degeneration is that person becomes blind. Tragic, but not life-threatening, okay? So they got that protocol approved to see if human embryonic stem cell research could cure macular degeneration. And after years of putting this, tweaking this protocol with mice and other lab animals and so forth, they got approved from the FDA. They started some trials and they were monitoring the patients, and they saw that it was going the wrong way, that they were beginning to develop tumors. So quickly they rescinded their protocol and stopped the research because it just doesn't work on the clinical side. And we say, thanks be to God, as pro-lifers, we say, thanks be to God that embryonic stem cells don't work because they're going after human embryos, all right? But it doesn't work just on the biology of it. Too much potential. And again, thanks be to God, there is a healthy alternative, which is in the adult stem cells, the ASCs, okay? Adult stem cells, because first of all, they're not pluripotent, they're multipotent, so they're already coaxed down into a particular organ system of the body, right? Number two, they can be autologous also, so they bypass the immune rejection. Oh, that's the other thing. The tumor also is going to cause an immune reaction on the rat because that tumor is 50% compatible with the adult rat, but 50% incompatible. And so it's going to mount an immune reaction. Mm-hmm. And so if you translate that into a patient, into a real human patient, now the patient, in addition to their pathology, have to deal with the potential of tumors and the potential of an immune reaction to the transplanted embryonic cells. Now, we can deal with the immune reaction simply by giving the patient steroids and toning down, or other medications that tone down immunosuppressants, which is done with transplant patients, right? They take immunosuppressants so that the foreign organ is not rejected. So we can deal, but then they have to deal with an immunosuppressed system. So complications. At any rate, there are already success in human trials with adult stem cells, all right? And I'll just leave it at this with the adult stem cells in general. There's this site, Stem Cell Research, which is being monitored by medical doctors, and also philosophers and theologians are involved in that site. But if you just punch Stem Cell Research, as one word, there's a site. There it is. All right. Oh, .org. Sorry. Yeah. No, it's going to go back. I have to write the whole thing. StemCellResearch.org. It's a site that is maintained by a number of doctors and researchers and other professionals involved in it. And it gives the latest news on adult stem cell research. And they have this little chart at the bottom here. To this date, there are 0 embryonic stem cell trials that are successful, but up to 73 successful trials in humans in different stages in the protocol, all right? And then you can go to this here, and it gives you the list of the various types of cancer of research that is going on at the different organs and tissues. All this list, and then there's another page, there's another area where they keep the articles. So they pick up the articles, right? Okay, people can explore the site, but basically it's by a group called Do No Harm. Okay, the Do No Harm group, which is, as you know, the first principle of medicine. And they have in one of these places, one of these links, they have the articles that come out over the years, over the decades of success with adult stem cells. And they have been saving all those articles in the site. So it's a very pro-life site, bottom line. But this is on the science of it. Okay, these are peer-reviewed scientific articles on the success of adult stem cell research. Again, at different stages of trial that is going on today. So that's a positive thing, and it's the healthy alternative, is the healthy alternative to the embryonic, okay? These actually work in clinical trials. Okay, couple more that need to be covered is the induced pluripotent, the iPSCs. This was Yamanaka. Shinji Yamanaka was a Japanese fellow, research scientist who was dealing with this quandary. He was a researcher in Japan with embryonic stem cells, human embryonic stem cells. And at one point, he was looking under the microscope, disaggregating human embryos precisely to obtain the blastocyst, right? To go into confluence and all that I explained. And he thought to himself, these blastocysts that I'm disaggregating look very much like my daughters looked like when they were blastocysts. That was his self-reflection. I remember this distinctly because it was in the early 2000s and I was at Purdue doing my second doctorate on the structure and function of DNA, and the big news hit, right? International news. So he said to himself, there's got to be an alternative. In other words, he was saying to himself, I am destroying human embryos. I am killing human embryos that look just like my daughters look when they were that size and that stage of development. So here's an honest person who was ground up in his conscience for killing these human embryos. Says there has to be an alternative. There has to be a healthy alternative to killing human embryos, to obtain pluripotent cells. And so he started looking at the factors. The factors are the proteins that are developmental proteins in early development, the first week of development, okay? The first days, going from zygote to morula, from morula to blastocyst, and then from blastocyst to gastrula. He was looking at that first 2 weeks and the regulatory proteins that regulate that development, that early differentiation. And so the race was on, because then other labs of the world got onto it and were looking for these regulatory proteins. It came down to 4, I believe it was 4 regulatory proteins that moved the embryo from the blastocyst to the gastrula. In other words, from pluripotent to multipotent, right? To the 3 germ layers. And the race was on, and he stayed in the lab day and night, and with his team, they worked on this alternative of discovering these regulatory proteins that are involved in early embryonic development, and they got it. And so, by inhibiting these regulatory proteins, the expression of these regulatory proteins early on, what happens is that the tissue de-differentiates, undifferentiates, goes backwards artificially against what nature does, against the one-way differentiation street, goes backwards, okay? And he actually got fibroblasts, which are part of the mesoderm, mostly muscle tissue, all right? He got human fibroblasts who are differentiated, fully differentiated. He got them to move back into pluripotent cells, but not the embryo, into pluripotent. So they are analogous to an ICM, but they're not an ICM because they come from fully differentiated cells, okay? So you follow? And that was the genius of this researcher. He undifferentiated, he de-differentiated fully differentiated cells. And then step 2, because that's not proof of the principle, the proof of the principle is that, okay, so what? Now we have these undifferentiated cells that came from fibroblasts. Now we have pluripotent stem cells, okay? Analogous to the ICM, but do they work? Can they be differentiated? Can they be redifferentiated into different cell lines? And the answer was yes. He got those undifferentiated cells to redifferentiate into some cell lines, okay? Back, for example, into fibroblasts. So he went back and forth from fully differentiated to multi-differentiated to pluri, and then stop there and move them forward again. And he got it just by playing with the regulatory proteins or the genes that code for those proteins. Follow? And that got him the Nobel Prize. Sweet. And so he developed these IPS cells, all right, induced pluripotent, and that's why they call IPS, because they are induced artificially in a lab. IPS, all right? But he got it. Pluripotent cells. without having to kill human embryos. All right? So we can say that ethically, they're not tainted, they're good, they can be used. Now, the challenge is that the vessels that are used for delivering these regulatory proteins, okay, typically are viral capsules, all right? So it's a shotgun thing. A shotgun in the sense that viral capsules, what are viral capsules? Well, viral capsule is just what it says. The capsule, so these proteins are encapsulated. You know, a virus is DNA with a protein code, basically. And what they do is they empty out the DNA from the virus and insert the regular protein of interest to then inject that into the particular tissue and the cells that they're working with. Because it's so super microscopic, right? So they're essentially using viral capsules as a syringe, as a microscopic syringe to inject the cells of interest with the precursors, with the regulatory proteins to do this IPS process. But it's a shotgun thing because obviously the technique is not sophisticated that they can clean out every single viral capsule from every single virus from the lot of virus that they're using. So some viruses may still be intact and have their own DNA or RNA, and therefore they'll be in the batch. So let's say that you have a batch of viral capsules where you have inserted your proteins of interest, the regulatory proteins, and are now ready to inject that into the tissue, the differentiated tissue that you want to undifferentiate, all right? To make the iPS cells. Well, that batch of viruses, all right, is 99.9999% encapsulated with the proteins of interest, but there is that 0.00001% of viruses that are still intact, meaning that they have their DNA or an RNA, so they are active viruses that are going to infect that 0.1. So when you have millions of viruses in this batch, that 0.0001% translates into 1 or 2 or 3 viruses that are active and alive and are going to contaminate the other cells, okay, with the wrong thing. And therefore, the challenge with IPS is precisely in the delivery mechanism, you know, that is risky. We can end up giving a virus infection to the patient. And so that's why it's tricky, all right? I understand, I haven't followed it a lot recently, in recent years, you know, but I understand that that has been worked out. And now they have other delivery systems that don't have to be viruses necessarily, et cetera. They have, but even all that has also been obviated. So you see, this kind of research is kind of cumbersome and challenging in the lab, very sophisticated, requiring very labor intensive and so forth, with a lot of checkpoints. And that's why he had to spend literally hundreds and hundreds of hours working in shifts overnight and so forth, because the race was on with other labs to get to the IPS product. You know, it did get him the Nobel Prize, but it's extremely cumbersome. And even though some of it has been streamlined, what happens now? Well, now we have this other technique, this CRISPR. And so CRISPR basically obviates all this, because CRISPR is another level of sophistication that is very sweet, research-wise. Because what CRISPR does is essentially, bottom line, with CRISPR, researchers can take a piece of DNA, a segment of DNA from any species, in principle, and insert that piece of DNA into any other species. Now that had been done in the lab before. It's called transformation. I did that when I was at Purdue with in bacteria. But that type of transformation that I was doing was shotgun. In other words, I would do it into a whole culture of bacteria, hoping that my DNA of interest would insert into any regions so they'd be amplified with PCR and all that, and purified for the research to get the protein expressed, the protein of interest expressed, okay? But it was shotgun. The interesting thing with CRISPR is that by keeping certain segments of the DNA, now this segment can be inserted into specific regions of the host cell, all right? So I can insert, in principle, I can insert a protein that expresses insulin into a patient that, well, it would be an embryonic patient. Let's say we are in a mouse model, into a diabetic mouse, into the embryo of that diabetic mouse, into the zygote of the diabetic mouse, in the region that is going to produce the pancreas. So it's not shotgun. It's not going to go into the liver or the brain or any other part. I can insert it into the genes that code for the pancreas of the mouse. So see, so in effect, in theory, I can heal that insulin deficiency in the pancreas because now I'm inserting the gene that produces insulin. All right, so this technique is, we call it elegant. All right, two-edged sword, because now we can insert essentially any gene from any species into any other species targeted into specific region. This can quickly translate into eugenics, right? Into eugenics at the molecular level. And so that's why it's a two-edged sword. What are we introducing, to whom, where, and who decides? Because obviously we need to deal with, here we need to deal with zygotes, not even more or less, because why deal with a cluster of cells if I can deal with a single cell where I have a single genome all concentrated at the zygote? But how was that zygote consulted? And we talk about human zygotes, and I was talking about human beings altering their genome, number one. Number two, when I do that alteration, assuming that that zygote is going to grow normal, it's going to be either a boy or girl who's going to be either a man or a woman who is naturally going to want to marry and have their own children. And so now I have inserted that gene into the gene pool, into the human genome. All right, and that zygote may or may not know because their parents may or may not tell them. And so I'm doing eugenics on the human genome, on the pool. And who has a right to change the human genome? That's a big unknown. That's a big, big challenging bioethical question. That takes it to the state of the art today. CRISPR, yes, sweet, elegant, but who has a right to decide? What genes? Are we better in the race? Are we doing positive eugenics, negative eugenics? Negative eugenics is healing disease. Positive eugenics is enhancement. Why not create a brighter brain? Why not create a bigger athlete? Why not create 8-foot people so that they can be soldiers, you know, with huge musculature? All right. And so who decides? Open question, open bioethical question. Back to, so Yamanaka did it, IPS, but now they've kind of, after all that effort, he did get the prize, but now this kind of CRISPR is now way beyond in sophistication, all right? And I mean, we can do CRISPR up in our Biosafety 1 lab here, you know, in lab Biosafety 1, because it can be done. There's a relatively simple technique. It's a type of transformation that I say, but it's targeted, all right? Simply by knowing the regulatory proteins, factors that are regulating that insertion. All right, so let's move forward to another type of stem cell that is also ethical, even though it takes a little bit of thinking, which is this, the umbilical cord stem cells, also known as cord cells for short, all right? So umbilical cord come from where? The umbilical cord. Now, what happens in the umbilical cord? First of all, what is the umbilical cord? The umbilical cord is a tube, several tubes that connect the baby with the placenta, right? The embryo with the placenta and the baby with the placenta, and there are arteries and veins that go through there, and through the placenta, the baby is connected to the mother, but now the baby is born. And so the baby is out, the placenta is out, and the umbilical cord is out. Inside that umbilical cord, there is a little bit of blood. It is fetal blood, right? In principle, it's on the fetal side of the placenta. It's not on the mother's side of the placenta. And so that's fetal blood. And there are stem cells in there. They're few, but real, and they are pristine. They're young, they're tender, they haven't been exposed to much radiation or other insults or toxins and so forth. In contrast with our stem cells that have been exposed already to radiation for X number of years and so forth. So they're very clean biologically, they're pristine, they're tender as the cells of the newborn himself or herself, right? The baby's already born. So these are the umbilical cord stem cells. Again, inside the cord. What happens to the cord normally? In a normal birth, a natural birth, the cord, the umbilical cord, is known as biological waste, right? It's cut, a knot is made on the baby's side, that knot is pushed into the belly and taped over, and that becomes the belly button, otherwise known as the navel. And then the rest of the cord is discarded, put in an orange bag as biohazard and probably burned, incinerated at the end of the day. And that is biohazard, is medical waste. But it's got the baby blood in there, and this little bit of blood that's in there has a little bit of stem cells, okay? They're fully compatible with the newborn, and so why not save them? And yes, they can be saved. So typically what happens is the couple will tell the doctor that they want to save their cord blood. They want to save the stem cells of the cord blood, right? And so then the doctor will tell the nurse, and the nurse will produce a kit, or the couple will buy the kit online, and which basically involves a syringe and some bags and whatnot. Maybe it's heparinized, I don't know. The point is that the nurse will then, when he or she has the blood, the umbilical cord, will draw out the blood and send it to the lab for spinning and separating, isolating the stem cells, and then those stem cells are cryopreserved. They're cryopreserved indefinitely because we don't know when the baby is going to use those stem cells. The idea is that hopefully the baby will never need those stem cells, because using a stem cell means that the baby at some point in his or her life got into an injury, an accident, or some illness or disease, and now healing needs to occur, right? Well, the cells have been saved, cryopreserved for years, decades, but they're there. So you need to follow with our mind's eye, you know, what's occurring in the process. But bottom line is that yes, they can be saved. Now, are they ethical or unethical? Yes, ethical. Umbilical cord, why? Because the baby is already born, not damaged, all right? The baby is not being damaged. I'll tell you, when I was in Boston preparing for medical school, getting into graduate school, I did a year's research at the medical hospital in Boston. The Catholic medical hospital there is St. Elizabeth Medical Hospital. It's a teaching hospital. It's associated with Tufts University Medical School, which is downtown Boston, and they use St. Elizabeth Medical Hospital as their teaching school, the medical teaching hospital. Anyway, big hospital. It's Catholic, Archdiocese of Boston, huge diocese. And I was doing some research there in preparation for getting into graduate school, looking for some recommendation letters, etc. And I was talking to one couple there, young couple there, having their first baby, and they were Catholic and pro-life, and they knew about me, so we were talking, and they got disappointed because they told their nurse, look, we want to save the cord blood of the baby. We want to get the stem cells. And the nurse told them, oh, we don't do that procedure here because this is a Catholic hospital. Imagine the level of confusion of this nurse, you know, that she thought, or he, I don't know if the nurse was male or female, but this nurse thought that that was an unethical procedure. They were in a Catholic hospital because of the embryonic stem cells, you know, or because of stem cells. And it turns out it's a very ethical procedure as long as the parents consent, because the baby cannot consent, you know, but it's for the good of the baby and there's no harm to the baby. There is expense to the couple, and that's the challenge, especially for young couples, all right? Because the procedure back then, I'm talking about almost about 15 years ago, was several $1,000s, maybe a couple $1,000s. There's a lot of markup between the kit and the protocol in the clinic or the hospital. So maybe a couple $1,000s by the time that the cells are extracted, spun down, and cryopreserved. And then there's the preservation itself, which these clinics, which sometimes are in vitro clinics, not necessarily, but they're the ones who have the cryo tanks, right? But they're all over the place. Anyway, how much does it cost? Maybe a couple $100s a year to preserve these cells, because these people are not charity, they don't do it for free, they're providing a service. And how long do the cells need to be there before they're actually used? Maybe decades. So those $100 are starting to mount up year after year, you know, and so it's expensive. It can become expensive for some couples. And as far as I know, insurance, medical insurance still doesn't cover it because it's considered elective. And so they don't want to cover it. So I was making the case for, especially for pro-life couples, to try to push this with insurance to at least cover part of it, because if we think about it, this is a type of regenerative medicine. And there would be an advantage to insurance. In other words, there would be fewer claims, and the claims would be for lesser amount, because stem cells, this is a type of adult stem cell that are the best type of stem cells in principle, because they're pristine, they're young, they're fresh, well, not fresh, cryopreserved, but fresh in the sense that they have not been exposed to insults, to either radiological or biochemical insults throughout life, because they're newborn, all right? So they have almost fetal quality. They have fetal quality multipotency, and in principle, they could be very good for healing going forward. So this child, this kid who has their stem cells preserved, in principle, would be less expensive to a medical insurance company, because they have these cells available for healing in case they get into serious illness or accident. And I'm thinking that statistically, it could lower the insurance liability on the company. And therefore, there is a vested interest in investing in the promotion of umbilical cord stem cells, saving umbilical cord stem cells by the couples, you know? So they could at least give some kind of partial coverage, insurance coverage, to incentivize couples, more couples, to save the umbilical cord cells, all right? Anyway, it's kind of a hypothetical thing. I don't know if some couples have followed up, and I've heard of a number of couples who do save their cord blood, but it can be done ethically. Okay, they're called mesenchymal stem cells. Like I say, multipotent, and this is just an example of the tissue that they could repair or heal going forward for this baby. Or siblings, because the siblings will also be some percentage compatible, and also parents. The parents could also benefit from this for this cord blood, because of the percentage compatibility there, at least 50% for each parent and so forth. So you can think of it in terms of a transplant. The best scenario transplant is siblings, right? Or parents, because of the genomic compatibility. Okay, enough. Questions, comments about stem cell research, okay, the distinctions and the possibilities and the good and the bad that is involved in that. All right, in 15 minutes or less, human cloning. All right, so again, human cloning, we have to make a distinction between reproductive and therapeutic cloning. But before we get to the actual cloning, well, the distinction between these two, we have to understand human cloning itself. All right, so the fancy word, the fancy phrase for human cloning is somatic cell nuclear transfer. That phrase describes what is going on. Somatic cell nuclear transfer, SCNT, all right? And sometimes it's abbreviated just down as, sometimes you just see NT for nuclear transfer because it's implied that it's from a somatic cell. So nuclear transfer, NT. Look what's happening. Here I have a, this could be an egg. This is an ovum that is an enucleated ovum, all right? So in other words, this ovum has, the nucleus has been plucked out. Yeah, so what do we have? We have an egg here, an ovum, that has been enucleated. In other words, with a very fine needle, it's a glass, typically it's like a glass capillary. The nucleus of this egg has been sucked out, all right? So that means that egg is enucleated. And a new nucleus, a somatic nucleus, is being inserted. And here is a somatic nucleus, all right? Somatic nucleus, by definition, is it haploid or diploid? Diploid, somatic nucleus. It's a body cell, right? Somatic, soma, cell, body. So a somatic nucleus comes from a somatic cell, which are all diploid. And we've got trillions of them, beginning with the skin, all right? So it's just a nucleus, a somatic nucleus. What does that mean? When I take an egg, an ovum, enucleate the haploid nucleus, all right? And substitute that pronucleus with a somatic nucleus. In fact, functionally, what have I generated? Zygote. I've generated a zygote without fertilization. Okay? So it's a type of asexual reproduction. That's why cloning is a type of asexual reproduction. Because it's generating a zygote without fertilization. The machinery here, by the way, it's pretty sophisticated. This blunt object that you see here, first of all, this is an ovum, so it's microscopic. We're talking about an average of 10 microns of diameter. Okay? It doesn't have to be human. It could be any other animal, mammal. So this blunt object here is a tube that is hollow, all right? And it's essentially the tip of a vacuum cleaner. It's the tip of a vacuum cleaner. What happens? This egg, this ovum is round and it's slippery, right? And it tends to slide away. So how are we going to get a needle inserted through the membrane if this egg is sliding? It's like trying to, you ever try to catch the olive with a fork and it slips away? You got to get it into a corner where you have the olive corner and then you can puncture it, right? All right. So that's what this suction machine does. Imagine the level of sophistication of this machine. This is a vacuum cleaner that is sucking on the ovum. And you can see that the ovum is bending in a little bit here. You can see it bending in a little bit, but this suction has to be controlled to such a degree, all right, that it neither lets the egg slip away to a little suction or sucks the egg in, too much suction. So imagine the level of sophistication of what this probe is connected to maintain a constant slight suction there to hold the egg in place and intact, to not compromise the cell membrane. A phospholipid bilayer, all right? Very thin membrane held in place. All right, so once we have the egg in place, now we come on to the other side with this syringe that is made, typically these capillaries are glass capillaries. Yes, a capillary is 1 cell thick or less, And this is how we do glass capillaries. I used to do this when I was at FAU in the 70s, working with some research there, and we had to make glass capillaries as a probe, all right? It's an electric probe, electrochemical probe. You take a glass tube that is hollow, just regular glass tube that is hollow, right? And you have your Bunsen burner. You bring the tube to the burner at the base of the flame where it's hottest, and the tube will turn red hot, and then you pull on the tube. You pull until the tube breaks, or you end up with 2 tubes, all right? Now, it's a quality of glass that the glass melts, because glass is actually liquid, and so it melts, and you pull, you end up with 2 tubes. The tube is hollow, all right? So if we follow the tube with our eye, there comes a point where I can no longer see the tip of the tube, right? I can no longer see it, but the tip of the tube is there because I can actually touch, and it used to fascinate me when I was doing this at FIU in the 70s as a young kid. I would hold the tube on one hand, you know, and I can follow the end of the tube. So the tube ended here, right, by sight. But then with my finger, I could touch the tip of the tube, and the tip of the tube was further away. It was like in space. It was in space. I couldn't see the tube, but the tube actually continued microscopically down to a capillary. And I knew that because I could actually touch the tip away here, over here in space, all right? And so these are glass capillaries, and the tube remained hollow inside. The capillary remained hollow inside. As long as I pulled quickly away from the flame and did not seal that tip, you know, if I leave it a second there, the capillary will seal in because it's liquid and will seal and become blunt like this. But if I just pull away, the tube remains hollow inside all the way to the tip, just like that. And it, in fact, becomes a syringe that is capillary, all right, in diameter. So that's how it's done. Anyway, that's the transfer there. The nucleus, the enucleated ovum receives a somatic nucleus. Sometimes they actually put the entire cell in there. Don't worry about taking out the nucleus. They just inject the entire cell. And the cytoplasm and the cell membrane and the cytoplasm of the invading cell is going to get dissolved away. But because there is no, there's no nucleus, it's enucleated, the egg is enucleated, and there's a nuclear membrane, double membrane, just like a cell membrane, to protect the nucleus remains intact many times. So that's the technology, all right? So basically it's a nuclear swap, all right? It's a nuclear swap from a pronucleus to a diploid nucleus. So we're restoring diploidy on this ovum. So essentially we have generated a zygote. And that zygote will be identical to whom? To the one who provided the egg or the one who provided the nucleus? Exactly. It's identical to the donor, to the nuclear donor, not the mother, not the one who provided the egg. The egg is just providing the cytoplasm, all right? And it's 100%, so that's why it's a clone. It's 100% identical to the egg, to the nuclear donor, okay? To the nuclear donor. All right, so remember Dolly? Not the singer, but the sheep. And there's a connection for the name. Tongue in cheek, we'll get to it. So this is what happened with Dolly. All right, Dolly was happening, I think it was in the 90s. Yeah, 96. At Roslin, the Roslin Institute, very prestigious research center in Scotland. And Wilmot, here's Ian Wilmot. And Ian Wilmot and his team in the lab were doing nuclear transfer, nuclear swaps. And so this is how they did it. First time done in a mammal. So we have, I think it's called a lamb, she lamb, okay, a she sheep to donate an egg. So we got an ovum from a sheep, obviously female. All right, then we take out the egg, we'll take out the pronucleus, haplonucleus. Now we have an enucleated ovum, Then we get another sheep and take the somatic cell, somatic nucleus from anywhere in the body of the sheep. All right, as long as it's diploid. And insert that. In this case, they use electricity, which is faster, cheaper, quicker. Just shock these two cells into fusing. All right. And by trial and error, at some point, one of these somatic cells is going to go into, the membranes are going to fuse. And the bottom line is that that diploid nucleus is going to go into the enucleated egg. All right. So now the fused egg is actually, this is a misnomer. Oh, sorry, fused cell. Okay. So this is now what? Zygote, diploid, clone, identical in genotype to this or this, to the donor, identical to the donor. Only the cytoplasm is from the donor of the cytoplasm of the egg, okay? But the regulatory proteins and all the mechanism for expressing is here. It's in the cytoplasm, obviously, okay? So that continues developing, the morula, blastocyst, then the blastocyst is implanted. This could be a third ewe, female, obviously, because of implantation. And then wait and see what happens if a baby lamb comes out. And it was Dolly. This diagram, I don't think is actually accurate for Dolly, because I think that what Wilmot did is he took the cell from the same mother. I forget now if it was the same mother, the egg donor, or used another lamb. I forget. I think he used the same one to try to maintain as much genomic compatibility as possible in the transfer, all right? But either way, and I think that he implanted into the same egg donor also. So potentially you can have anywhere from 1 to 3 sheep involved in the process, right? 3 sheep as illustrated here. One is the egg donor, the other one is the somatic nuclear donor, and the third one is the surrogate mother, the surrogate womb. That's 3 sheep. Or you can narrow it down to 1, where the single female becomes the egg donor, the somatic nuclear donor, and the mother, not surrogate, the mother of her own zygote going forward. You follow? Okay? All right. So he did this trial and trial and trial until eventually he got one baby lamb that survived and survived to adulthood. So where's the proof of principle? The proof of principle is that this baby lamb, to be considered normal, has to achieve what? Reproductive success, has to have offspring. So until Dolly grew up and was mated, obviously had to be female. So this, the somatic cell had to come from a female, all right, to produce a female embryo. So only when Dolly was mated and mated successfully and had offspring that were viable, all right, that was the proof of principle that it could be done. So it took several years, but they got it. What people don't know is that it took how many trials? Was this in the first trial, the first dozen trial, the first 100 trial? It took about 250, I think it was 258 trials to get a viable Dolly. So 258 attempts that did make it. Typically, they were aborted at some point because they just didn't, the pregnancy didn't follow. So it took about 258. Since Dolly, many other mammals have been cloned. I remember the next one was, or one of the following was the cat. It was called Copycat. And then it was the mouse, and then it was, the dog was very difficult to clone because for some reason the female cycle on the dog is very difficult to pinpoint when the female is actually ovulating, all right? And so the dog was difficult, but they got it. And of course, when this came in the horizon in the 90s, I said to myself, well, cloning a mammal is cloning a mammal. And biologically, we're mammals, so we're not far away from cloning a human here since we got the technique for a mammal. All right, it was big, big, huge news back then and so forth. And then what happened? Turns out that Dolly started developing as an adult senile symptoms prematurely. She developed arthritis and was, they could tell that she was in pain, you know, and she was young chronologically, but she was aging prematurely. And that has become a kind of a standard pattern for this type of cloning, all right, reproductive cloning. It stands to reason, it goes with the intuition because the somatic cell, the somatic nucleus is already aged. You know, it comes from a born mammal or born animal. And so that nucleus, essentially what happens here is that this nucleus undifferentiates, dedifferentiates to pluripotency. In order to get a blastocyst out of the zygote has to be pluripotent. And it's the nucleus of the zygote that is pluripotent, right? So here, yes, this fully differentiated nucleus undifferentiates, dedifferentiates, like Yamanaka did in the lab, but this goes all the way to pluripotency, and then forward again through differentiation into a fully differentiated animal. All right. And so, but it's a forced process. It's an artificial process in the sense that this would never happen in nature. When you see a somatic cell fusing with a gamete, right? And so apparently they age faster and they become old prematurely. And so the bottom line with Dolly, what was the end of Dolly? She was euthanized. She was killed. She was euthanized by the team because she had aged prematurely. Now she's in pain and she's developed arthritis. She has more difficulty getting up and walking around. And, you know, poor Dolly, that's inhumane. So they killed her. I think that this is actually the Dotto, because now she's preserved. They also, what is that called? Taxidermy, they preserved her, okay? So they euthanized her and then they preserved the skin and the hair. And so this is the taxidermed Dolly right there, right? I think she is, yeah, she's no longer living. But anyway, that's what happened. It was basically the proof of principle that it can be done. This was the first mammal. And since then, many mammals are being cloned. And this has potential in animal husbandry. In the cattle industry, for example, a cow that is giving prodigious amounts of milk, you know, 10 times more milk than the other cows, well, maybe that nucleus is worth cloning to see if we can make many more cows that produce more like that. And the same argument can be made with many other animals that are kept in cattle, in animal husbandry, all right? It can be made for birds also, for chickens or whatever, a chicken that gets to be bigger, etc., more healthy. Anyway, all kinds of positive things could spin out of here. But then when we talk about humans, okay, that's where it got very nasty, because for humans, reproductive cloning here's a diagram for reproductive. It basically follows the same process, or the idea is to generate a baby for a couple that cannot have a baby. All right, so that's why it's reproductive. So we do cloning, human cloning, for the purpose of generating a baby for a couple or an individual who cannot have babies on their own, or who don't want to have babies on their own, because this is not illegal, and therefore, as long as they can pay for it, again, we get the scenario, how many parents can this baby have? Well, they can have the mother, they can have one mother who is the egg donor, they can have another parent who is the somatic cell donor, and then they can have a third parent who is the surrogate mother, the rental womb, That's the third parent. And then they can have either the individual or the couple who is paying for the process. So again, up to 5 parents the baby can have, all right? Or the baby can have a single parent. In other words, the woman who donates the egg and uses a cell of her own body to generate the zygote from one of her somatic cells, and then implants that embryo into herself and carries it to term. So this baby can also be 100% identical to her mother. She will always be a female. But chronologically, she may be 10, well, not 10, sorry, maybe 20, 30, 40 years apart to her twin, to her identical twin, to her monozygotic twin. So it's aberrant. I mean, it's grotesque, right? And so many scientists spoke against reproductive cloning for humans, basically, mostly based on the fast aging process, the fast aging, that this baby will age prematurely, and maybe as a teenager or as a young adult will develop senile qualities, including arthritis and maybe some mental also senility. And so because of that, many scientists of the world spoke against reproductive cloning. It is inhuman to clone a human for reproductive purposes. But, for therapeutic purposes, it's a different story. For therapeutic purposes, many of these scientists who spoke against reproductive cloning for humans are 100% in favor of therapeutic cloning of humans. So what is the therapeutic cloning of humans? Essentially the same basic technique. We end up with a zygote, but now the zygote we allow to grow in the lab to the blastocyst the same way, because we need a blastocyst for implantation, right? But instead of implanting the blastocyst, we go after the ICM for embryonic stem cells. And this, in their mind, in the mind of these scientists, this is a way of generating embryonic stem cells without generating embryonic embryos, because these are cloned eggs, right? These are enucleated eggs with a somatic cell nuclear transfer and with nuclear swap. So there's no fertilization, therefore there's no human being. And in fact, there is a human being that was generated asexually by cloning, all right? So the argument here is that this would be a way of obtaining embryonic stem cells without killing human embryos. Well, they are killing human embryos. It's just that the embryo was reproduced, was generated, was created asexually instead of sexually, all right? So really, frankly, in full honesty, it's two-faced. It's not accepting the biology, the basic biological facts of the fact that when we do a nuclear swap on an egg, we have a zygote. We end up with a zygote. The first cell of a new individual diploid, and if it undergoes mitosis, then you better believe that's a somatic cell. That's a diploid cell of whatever species. So again, we would be against, not only that, I mean, the second offense here, the first offense, of course, is cloning a human, is generating a new human being artificially by nuclear swap. Who has the right to do that? But secondly, not only that, this particular human being is being created in the lab, is being manufactured specifically to be killed to obtain his or her stem cells, okay? So the double offense here is that we are manufacturing a human being in the lab, we're manufacturing a human zygote precisely to obtain his or her embryonic stem cells. In other words, to kill that zygote, targeted for being killed for their ICM. So the double offense. You know, at least in reproductive cloning, we can say, well, at least the end is to have the baby live, right? But here, the end is kill the baby to obtain the embryonic stem cells. So double offense, right? Of course, on a utilitarian mentality, this is spectacular, fantastic, because it's a way of obtaining these embryonic stem cells without fertilization, without harming human embryos, et cetera, et cetera. So that's the thing about cloning. Either way, the big question on human cloning is who has a right to clone a human being? Who has a right to generate, to manufacture an identical human being, you know, from another human? And the answer is nobody. Only God has a right to generate a human being, and only couples have a right to generate a human being in a natural process in which was intended to begin with, which is the normal process of fertilization. All right. Now, okay, I think it's pretty clear now. Again, the community, the scientific community has walked away from human cloning or from human cloning because it's not that practical. It's still controversial. There is research going on here, and to the tune of several $1 million. There was a proposition in California. I think it was Proposition 71 or Proposition 8. Proposition 8, California. No, maybe it wasn't the right truth. No, then it was 71, maybe. I forget the number. One of these propositions in California, the state was able to obtain millions of dollars funding for stem cell research. Great, here we go. The Institute for Regenerative Medicine, CIRM. Okay. This was $3 billion in 2004 for human embryonic stem cell research in California, $3 billion out of taxpayers. But then what happens is the administration changed at the federal level, and a new president who essentially allowed federal funds, because this was under the gag rule. In other words, the federal funds could not be used. Bush W inserted that federal funds could not be used for human embryonic stem cell research at the federal level, but state funds, you know, feds have nothing to say on that. And so different states try to get these propositions out to get state funding for embryonic stem cell research. California was successful. They tried it here in Florida. We started a campaign against it. And then the administration changed and we had a new president, and the new president essentially by executive order opened the floodgates of federal money to human embryonic stem cell research and human cloning and all this. And so the states kind of gave up because now they had federal funds, big money coming in for that research. And so that's what happened. But since they're not getting much results precisely because of the issue of pluripotency being too much potential, then on the science of it, many scientists have walked away. And of course, now with CRISPR and the adult stem cell research combined, that's much more, not only is it ethically palatable to the population at large, but it's much more successful, clinically speaking, and research-wise, okay? So thanks be to God, the research has gone that way, which happens to be ethical, not because necessarily they want it to be ethical, but because it's the one that's actually working. So if it's working, you know, it can be a utilitarian mentality. Anyway, wanted to cover stem cell research, wanted to cover cloning, so now you have the background. Question, comments? No? All right. One last thing. I end with this because it's kind of ironic and it's tongue-in-cheek, but at the end of the day, it's anyway, it's chauvinist. Why was Dolly named Dolly? Why, of all names, okay? Just tongue-in-cheek. This is what happened. Because Wilmot, yeah, and so it was the same U. Wilmot wanted to be successful, and so he was trying to minimize the incompatibility, the genomic incompatibility between donor and recipient, okay? And so he actually used the donor cell came from the udder of the U. Okay, so this is for people. you know, when I see sheep, I see them from a distance and I work with sheep or that, but in Scotland, you know, they have a lot of sheep and they work with them. So it's the udder of the ewe, the female lamb, right? A she lamb. And what's the udder? The udder is the mammary glands of the sheep, of the cattle, right? The mammary glands. So it is a tongue-in-cheek reference to, in the words of Ian Wilmot, the prodigious mammary glands of Dolly Parton. Okay, so here is a reference to the prodigious mammary glands of Dolly Parton in Ian's words. You can look it up online, but that's why Dolly was called Dolly. Dolly the sheep after Dolly Parton, because the somatic cell came from the udder of the ewe lamb donor. Anyway, funny for him at the time, in second thought, offensive to Dolly Parton, whom I happen to think is a great actress, very ethical person. Have you seen Steel Magnolias? You seen that movie? Yeah, I know it dates me, but that's a fantastic movie. No, Steel. Check it out. Steel Magnolias is a fun movie, but I think it's very, it's a lot of value system, how these women survive hardships. And Dolly Parton is one of the main actresses there. Okay. Anyway, that's the lecture for today. So if there are no more questions or comments, we'll close it here. And we'll have our last lecture for the beginning of life course next week. And then remember, in 2 Saturdays, because we have no lectures, there's the opportunity to come to the forest. Hopefully it will not be raining. March 6th between 9:30 and 12:30. You can come from any of that time if you have the possibility, okay? Look into the other options of internship that I suggested. And maybe you have something, Chris, in your area that is beginning to open up for some kind of internship in bioethics. We can talk more about that offline, certainly, but please be proactive in looking for these internships because December is fast approaching. All right, anything else? Thanks again. I'll stop here and see you next week. Thanks again.
Thanks so much, Professor. Have a good one.
You too. Bye.
Mm-hmm.